Welcome to Hot Chips 26. Tutorial 1. Emerging Trends in Hardware Support for Security.
I am Sam Nafziger, the program co-chair for this year's Hot Chips. And Ruby Lee will be the session chair for the security tutorial. Ruby is a familiar name in the industry, very well known for her work in security, multimedia, and computer architecture. Her current research is in security-aware computer architecture at Princeton University. Before Princeton, Ruby was chief architect at Hewlett-Packard for processor and multimedia designs, playing a big role in the architecture of the PA RISC chips, which had a big impact on the industry over many years. She co-led the Itanium multimedia architecture and created the first security roadmap for enterprise and e-commerce security at Hewlett-Packard. She is an ACM fellow and an IEEE fellow with over 120 patents. So we are very pleased to have Ruby here to chair this tutorial and deliver a key part of it. Please join me in welcoming Ruby.
Thank you, Sam. Okay, can you guys hear me all right? Okay, so I'd like to welcome you to this Hot Chips security tutorial. Actually, John Davis helped arrange this, but he's not able to be here today, so I'd like to welcome you to this for him. So the motivation for this tutorial is that cybersecurity is becoming very important as our daily lives, involve using cyberspace all the time, including our financial competitiveness and national security needs. So in the past, cybersecurity solutions have been in software, and this has not always worked very well. As you can see, there are increasing attacks every day. So it seems that hardware has not been fully utilized to improve cybersecurity. And today you see more and more people, including hardware vendors, being very interested in seeing how hardware can help improve cybersecurity. So that's what this talk is about, this whole tutorial. First, in case you are new to cybersecurity or even to security in general, we are going to give you some basic security framework for thinking about how to design secure systems and how to evaluate secure systems. And then we are going to talk about several security issues with speakers from ARM, AMD, and Intel, and they will talk to you about secure system design and what are the threats that industry has already attacked and what are the defenses that have been used. And then I will end with a short survey of university research done in hardware security. This will be fairly packed, and you will not necessarily understand everything, but there are slides there for you to follow later on. So the speakers would be myself, and then Vikas Chandra from ARM, Leendert VanDoorn from AMD, and David Durham from Intel, and I will introduce each one of them in time. At the end of the day, we have a break at 11:20, and at the end of the day at 12:50, we will have 10 minutes for questions, okay? And if you have more questions after that, there are some security tables reserved at lunch, and you're welcome to join the speakers at lunch, okay? Now I would like to start with the security basics. I'm a little short. I don't know if you can see me over the podium. So, what is security? We are going to talk about what exactly is security and what is a threat model, and how is secure design different from normal hardware design. What are security policies and what's access control, and how cryptography can help us in secure system design, and finally a little bit about security protocols. Now this will be a whirlwind overview, so I'll try to touch the highlights. So what exactly is security? Everybody understands confidentiality. There are said to be 3 cornerstone properties of security. The first is confidentiality, the second is integrity, and the third is availability. And I help people to understand this by remembering the acronym CIA. Okay. CIA, not for the agency we all know, but CIA for confidentiality, integrity, and availability. So confidentiality just means that you try to prevent the disclosure of sensitive or secret information to unauthorized people, okay? And an example attack would be eavesdropping. If some unauthorized person eavesdrop on your confidential message, that is a breach of confidentiality. Now, integrity means that the data was changed without the authorized people being aware, without people being able to detect it, okay? So an example of this might be malware or viruses that somehow enter your program, okay? And so your program is, in a sense, changed. And the malware does something else, okay, that is not expected, like write your password file or read it or something. So a simple way to try and remember is that confidentiality breaches happen only with reading, okay? Whereas integrity breaches happen when something is modified or written, okay, without detection. All right. So the third thing that is a cornerstone of security is availability. Now, not many people realize that availability is very much a security property, and that is when your resources in your system is available, when legitimate users want to use it. And denial of service attacks happen when the legitimate users cannot access their services and resources. Okay. So this is all you must remember about security, the cornerstone properties of security. Of course, there's many, many other security aspects. For example, access control policy is to prevent unauthorized people from accessing your protected resources or services, okay? And we'll talk a little bit more. It means that you've got to identify the subject, okay, before you can tell whether he is authorized to access that resource or not. Coming big on the scene is accountability and attribution. So if some vulnerability happens, who is accountable? Is it the software vendor, the hardware vendor, the system vendor, the user who didn't set proper security measures? You know, who's accountable? And attribution is, if something bad happens, how can you find the real attacker? Okay, who is the attacker that caused this problem? Non-repudiation is the denial that something happened. Denial, suppose you ask your stockbroker to buy shares, and then later you say, I didn't ask for that. Okay, that's repudiation. So if you make a request and it's non-repudiated, you should not be able to deny it. Okay. Anonymity is the ability to carry actions out without being identified. And privacy is the right to determine which of your personal information should go out to whom, all right? So there's a distinction between the confidentiality aspect of security and privacy, because confidentiality usually means the obligation to protect certain sensitive information, whereas privacy is like the right to see who gets your personal information. So in order to see what's different about secure system design, I came up with this little step-by-step methodology for what you should do. First, you should describe usage scenarios. Okay, are you talking about e-banking, or are you talking about losing nuclear secrets? You know, or is it a digital rights management problem? All right. Try to define succinctly what is the security problem you're trying to solve. And then here's where the new part is. You have to define the threat model. Because in general, we can't solve every possible threat all at once. So you must define, are you really interested in confidentiality and not so interested in availability and so forth? Okay, what's the threat model? How much power does the attacker have? And then you have to define what's called security policies. So security policies are not necessarily just done by the engineer. You know, the executives of the company or whoever also have to be involved in defining these security policies. It says who gets access to what and when, all right, and what's allowed, or to what degree do you allow false positives and false negatives. Right? And then you would define the security mechanisms to go with these policies. Then you present the entire architecture with your security mechanisms integrated, and you would try to evaluate whether the security works or not, you know, with test cases and as well as you can with other examples. And then you should evaluate it for all the common hardware design features like performance and power and usability, how deployable it is, and so forth. And then iterate, if necessary, the design of security mechanisms and so forth. So the main difference is the threat model and the security policies. So I would like to go over that in a little more detail. So a threat model says what are the threats that this solution considers most important, okay? It should also say what are the threats not considered, okay? You can't be completely exhaustive about those not considered, but at least mention we're not talking about side channels or something like this, okay? An attack is like an instantiation of a threat. So you might say a threat to confidentiality, and key logging is an example of an attack, okay, on a confidentiality breach. So that's what an attack is. And you always hear about threats and attacks talked about in general. So an attack that is successful will violate a security property of the system. It might violate confidentiality or integrity or availability or accountability and so forth, okay? So hardware designers now have to think, in addition to performance-based design and power-based design, what's threat-based design, okay? Threat-based design means thinking like the attacker, not just making the functionality work, but how would the attacker try to break the system? And if the attacker is breaking the system, how can you prevent this according to the security policies defined? So typically, I would now go into threats and attacks, but I'll leave this for the individual speakers to describe different threats and attacks, okay? There's databases of attacks and vulnerabilities around, many such databases. One is the CVE done by MITRE, and there's many, many others, okay? So what's important to know is there's no such thing as absolute security. It's an arms race. The better you get at defenses, the smarter the attackers get to go around the defenses, and you have to put other defenses and so forth. This is no different than, for example, viruses in the human world. You know, you think you've got rid of some virus with vaccinations, and then a couple of years later it comes back again, all right? So it's an arms race. And the idea is, how high do you raise the bar for the attacker? If it's going to be so costly for him, and if he's sure to be found, then he might not do it. But if it costs him nothing, and he can get a big payback, his return on investment for the attacker is very high, and so he's going to do it. So what we want to do is we want to make the attacker's life a lot more difficult. Not impossible, but a lot more difficult. Raise the bar for him to successfully attack the system. Now, what's the difference between security and reliability? They all want a dependable system. The difference is that in reliability, you have these statistical and characteristic behavior of how components fail and so forth. But in security, you've got attackers who are very, very crafty and wily, and they don't follow any statistical patterns. So in a sense, you might be able to use some of the reliability mechanisms, but you can't count on statistical distribution of attacks. So a word about the difference between security policies and security mechanisms. Security policies specify what and who is allowed to access what resources or information at what time. And the security mechanisms are the means to enforce the policy, okay? Another word about the difference between trusted and trustworthy. Okay. Trusted means that that software or hardware or networking component must work and must not be infiltrated by attacker or changed by attacker in order for the security policy to hold. Okay? So you trust that software component. Maybe it's the operating system, maybe it's the hypervisor, maybe it's the hardware processor, okay? But you may not trust the disk, for example, or the network. Trustworthy, on the other hand, was the system even designed to be secure and dependable in the first place? So the two are not the same at all. So what's the problem today? The problem is today the operating system is trusted when actually it never was designed to be trustworthy in the commodity OSs. So think about this. It's like a 5-star general is trusted to maintain military policies. But if he's leaking secrets to a Russian spy, he's not trustworthy. Now, similarly, you might have a janitor who's very honest and trustworthy, but he is not trusted with top secret information. So the two are not the same, all right? For security to work, there's got to be what's called a trusted computing base, TCB. And this is the set of software, hardware, and networking components that must be trusted and must not have bugs and must not be infiltratable for the security of the system to work. And so you like this to be small, so maybe you can prove it and there's less bugs and so forth. But it's a very difficult thing. Today's commodity systems are by no means designed in a trustworthy way, and nor can one really count on their trusted computing base. So this is what we aim to improve. So next, I will move on to security policies. Right? What are security policies? Just in general, you can consider hierarchical policies, which on the left we call multi-level policies, and on the right we consider multilateral policies. Okay? So the stuff on the left is traditional security, multi-level security, where each higher level of security it has access to more information, all right? So for example, the Department of Defense model on the left has unclassified at the bottom level, no security, and then confidential level, then secret level, and then top secret level. So the idea is the top secret guy can see everything, but the unclassified guy can only see unclassified information, cannot read confidential, secret, or top secret information. Similarly, the confidential guy can only read confidential and unclassified data, but not higher, like secret or top secret data. And this is a hierarchical structure where it's very applicable to, for example, military and so forth, and also to companies and enterprises. But sometimes it's not so practical when there aren't hierarchical security levels. For example, in a law firm, you may not allow one lawyer to work on a company that has conflict of interest with another company. So these two companies like A, B, and C are not hierarchically secure, but more multilaterally secure, right? And so there's generally multi-level security policies and multilateral security policies. So let's take an example of multi-level security, MLS. So I think I've explained this already. MLS is often called a mandatory access policy. That is, you don't get to choose which level you are in. You get classified as a subject. You get cleared into a certain level. So this person, Tom, is cleared into top secret level, which takes longer to clear him for clearance than, say, another one who's only cleared into secret level, all right? And objects are similarly classified into these levels, all right? And you can see on the right that companies will also have the same hierarchical access to information, with CEOs having the most and employees less, and perhaps the customers even less access to company information. So what's a typical MLS policy for confidentiality? And so this is the very well-known Bell-LaPadula model called BLP. It's to prevent confidentiality and to prevent unauthorized reading of data, okay, or programs or information in general. And interestingly, it has only two rules, all right? So the two rules are that no subject may read data classified at a higher security level than his clearance. So that makes sense, all right? It's called no read up. You can read down, objects of less security, but you can't read up above your clearance level, right? But there's also a write rule, and it's called the star property, right? This says that no subject may write down to a lower level, okay? So this seems a little interesting. It's the no write down rule. So BLP, a short form to remember, is no read up, no write down. Now, no read up is clear. You classify a lower level, you can't read you're cleared at the lower level, you can't read higher security classified things. But why this no write down? Well, if you don't have the no write down rule, then let's take this corrupted general, General Smith. He's cleared at top secret, so he can read top secret documents. But if he is allowed to write down to an unclassified file, then Vladimir, the Russian spy, could read that unclassified file, okay? Because General Smith could write some top secret information into the lower classified file, okay? So that's why you need the star property. Now, similarly to BLP, there is an MLS policy called BIBA that is for integrity, and it's almost like exactly the counterpart of BLP. Instead of no read up, no write down, it is no write up, no read down, okay? And you can read about this in many books, and especially there's also a book that I wrote on this that you can read about this, and I'll mention that at the end. Now, very often the MLS by itself is not enough because there's too many people classified top secret, for example. So there might be code words added in each level. And these code words are like multilateral compartments within one MLS security level. So for example, there may be code words for Afghanistan, and there may be a code word for Gaza Strip, something. So only people who are at that security level and authorized with that code word can access that data. On the other hand, in the right column for multilateral security policies, you have confidentiality policies like Chinese wall, okay, which will prevent conflict of interest, access to different companies' documents. And you have an integrity policy called Clark-Wilson, which all the banks use even before the time when computers got popular. It's a sort of a cross-checking version for integrity. And then you have, lots of examples of like the British Medical Association's policy for accessing online medical records. Okay. So these security policy models are interesting to study because they tell you how to think about security policies, but they are only models, all right? In real life, security policies can be very, very complex. For example, you've all seen privacy policies that companies send to you, or the HIPAA policy for medical records and so forth. These are multi-page documents which are very complicated and not so straightforward like this, okay? But these help you to understand how to think in general about hierarchical security levels as well as lateral security levels. So in general, these policies would be translated into access policy languages and then interpreted by software, or they could be translated into XML. All right, now if we went back to the security design methodology, once you've defined your policies, you've got to define your security mechanisms. Well, the most important mechanism is access control. Access control can prevent the illegitimate guys from reading your confidential information or from being able to modify your high integrity data. Or access control can also provide a means for availability. You can prevent more requests if your system is getting too loaded or something, okay? So access control first has to have authentication. Who is the subject? And typically, this has been answered in 3 ways. You do authentication by saying what you know, like your password, okay? What you have, maybe you have some sort of key fob or something like this, okay? Or a smart card with something. Or you might have a private key in a smart card. And what you are is like biometrics, okay? So typically, you would use at least one of these methods to authenticate the person or the program or the machine, okay? But once you've authenticated the person, then it's a question of what is the person allowed to do, and that's called authorization, okay? So in a sense, it restricts the actions of an authenticated user or program, all right? And typically, for simple access control systems, you have an access control matrix. In the rows of the matrix, you have the subjects, all right? In the columns, you have the objects. And each entry will say whether that subject is allowed to read or write or execute that object. And there may be other properties like, can he delegate his rights? Can he start a new right? Things like this. So access control matrix is often used, as we know, in Unix file systems and all that, and kept either by rows or columns. If it's kept by rows, that means for every file object, you will say who's allowed to access that file, okay? If it's kept by column. If it's kept by row, it's called a capability system, where each subject will have the capability or the right to access certain objects, like files or programs or services, okay? So access control is based on authentication and authorization, and I try to help people to remember this by remembering AAA, okay? Not Automobile Association of America, but access control for authentication and authorization. So now you have CIA for the cornerstone security properties and AAA for a key mechanism to achieve these things. So there's all kinds of access control. For example, mandatory access control, as I've discussed with the MLS system, where the system, in fact, says what's the access control policy, like BLP or BIBA or something. And then there's discretionary access control, which are all familiar, like in Unix file systems, the user says who gets access to the file, right? And there's all kinds of other access control types, like role-based access control. So if Tom Smith is acting as a system administrator, he gets this access in his role as system administrator. But if he's just acting as a soccer dad, then he doesn't get that same access, all right? And there's an interesting thing called originator-based access control, or ORCON, where it says that some policy defined with that file or that object must hold throughout its lifetime, all right? And that has been very hard to implement in general. So we've covered a bunch of stuff, and like threat model, the secure design methodology, what are security policies, and access control. So now we'd like to look at a tool, cryptography. To us hardware designers, cryptography is a very useful tool. And I would talk only about 3 of the most common cryptographic methods, which is symmetric key ciphers, hash functions, and public key. So Symmetric key ciphers, we are interested because, of course, they're useful for confidentiality. And hash functions are useful for helping to protect integrity. And public key ciphers are very essential for this authentication business. In fact, public key ciphers help you to have a longer-term digital identity in cyberspace. And it's very useful for digital signatures and non-repudiation of requests and things like this. So I like to call this cryptographic access control. So instead of, if you have a protected file, instead of having a guard that will see who's allowed to read this file or write this file, you just encrypt the file and throw it in the public networks on public storage, okay? But you keep the key. Okay, this is cryptographic access control, all right? You keep the key so that to the unauthorized person, it's all gibberish, but to the authorized person, it's not. So when you talk about cryptography, and we'll start with symmetric key cryptography, we just need a little bit of terminology, right? So the plain text is the unencrypted data that you want to protect. You go through a cipher to encrypt it with a certain key, and then it's called ciphertext when it's encrypted, all right? So now you can send the ciphertext wherever you want, but keep the key secret. Symmetric key cryptography means that when the receiver gets the ciphertext, he used the same key to decrypt the data, all right, and get back the plain text. Now, this seems very obvious, but in public key cryptography, you'll find that these two keys are different, all right? So in symmetric key cryptography, the key to encrypt and the key to decrypt are the same. Now, block ciphers are one form of symmetric key ciphers, and we know them well as things like AES, the Advanced Encryption Standard, or DES, you know, the older data encryption standard. Both standards put forth by NIST after lots of competitions for the best symmetric key cipher. And if you try to look at their generic structure, they all look about the same, all right? You take the plain text, you go through some preamble, and then you go through several rounds, okay, of computation, and then finally you might have an epilogue thing, and then you get the ciphertext. Okay. So what's different is how many rounds and what's in each round, all right? And then you see this secret key that comes in there on the right, okay? Secret key will come in, and that will get expanded into a round key for each of the rounds, all right? So this is what a typical block cipher looks like. There are also things called stream ciphers that are very useful, like for mobile phones and things like that. But I want to emphasize that you don't just go implement a cipher and think you've got security, right? Because there's things called modes of operation, even just for block ciphers, all right? So on the very left, you see what I just described. It's called electronic code book. You divide your message into fixed length blocks, and you encrypt each block independently. Well, what's the problem with this? The problem is that the same plain text block will result in the same ciphertext. So if you have a lot of same plain text blocks, you can see the same ciphertext and you can get some information. And with a little bit of cut and paste and all this attacks, you can figure out a lot of stuff from the encrypted data, even if you don't have the key. So modes of operation try to prevent this, all right? So in the middle, you see what's called cipher block chaining. And cipher block chaining says you take the encrypted thing of the previous block and XOR it with the next plain text block before you encrypt, okay? So now the same plain text block will not result in the same ciphertext. And the last mode of operation, which is very useful for computer designers who are interested in performance, is called counter mode. Because, of course, the delay is in the encryption, right? So now what happens is you take a counter, okay? Each time a counter advances is a different number, right? You encrypt the counter. Now you've encrypted all these counters ahead of time. And when your plain text comes, all you have to do is a simple XOR with the encrypted counter to get the ciphertext. So that's fast, okay, on the critical path. But there are, of course, problems implementing each of these. Not the left one, the simple-minded electronic code book method, but the other two. And this is where hardware ingenuity would come in. Of course, those can be implemented by software as well. But if you want to implement hardware ciphers, you also have to implement all these various modes of operation. Okay. So now we'll move on to cryptographic hashes. And I'm going to go through this really fast. So the idea is you take your message. No, first you start on the left with IV. That's an initialization vector. It's actually a constant, all right? Then you take your message in fixed length chunks, like 512 bits, and you perform this operation F on it, okay, until finally your constant initialization vector becomes your hash value. And the amazing thing about hash functions is that even if you change one bit of the input, the hash output will be completely different, okay? There's no predicting that if I only change this bit, my output will be the same except for certain small parts, no. So the good thing about hash function is it gives you a fingerprint of the message or the file. Even if the file is 10 gigabytes, it will come down to a fingerprint of whatever the hash length is. And these hash lengths are anywhere from 128 bits, 160 bits, or 256 bits, or at the most secure format, 512 bits. So typically think of like 128 bits or 256-bit hash, okay? So that's a lot smaller thing that you have to keep to make sure that your file hasn't changed or your program hasn't changed, okay? So it's very good for what? Data corruption. So if you hashed your good program and later on some malware got in or someone maliciously changed the program, you take a hash again and it's not the same, it's changed, okay? Another thing we have used it for is as the identity of a software module. So very often software modules have different names and all this, but if their code is identical, they will have the same hash, all right? And the hash, everyone knows the hash function. So what if the attacker generated a new message and created a new hash? Well, that's no good. So you can have what's called keyed hashes, where you add a key to the message when you do the hash, all right? Now, when you're trying to hash the whole memory, for example, 16 gigabytes of memory or something, and every time you change one cache line, you have to hash the whole thing, it takes too long. So there's things called memory integrity trees, where you would hash the cache lines, and then you hash the hashes of cache lines, and so forth, until finally you get the root hash. And the root hash is the only thing you have to keep securely. Because if the root hash is not correct, then something below is not correct. If the root hash is correct, then everything below has maintained integrity. So how is this used in general in hardware? In secure processors, we consider the processor to be the only hardware component in the trusted computing base. in order to minimize the trusted computing base. And the memory is untrusted. So within the processor, you can have plain text, because that's the definition of a trusted security perimeter. But outside, once you try to flush a line out of the last level cache, you got to encrypt it. And if you're interested in integrity, you got to hash it also. And then later, when you're bringing in lines into the last level cache, you will decrypt if it's authorized, and you will verify the hash to make sure that the attacker didn't change the memory, okay? Now, I'm going to have to go very quickly over the rest of this, but the most important thing in symmetric key ciphers and hash functions is the key management. Okay, you got to protect the keys, all right? Now, what is public key cryptography? As I said, in public key cryptography, also called asymmetric cryptography, you use one key to encrypt and a different key to decrypt. So these are called public key pairs, a public key, which everyone should know, and a private key, which determines your identity, okay? So if you want to send some encrypted data that only the person with the private key can decrypt, you will encrypt it with the public key, and only he has his private key can decrypt. So the private key is like your digital identity, okay? And similarly, if you want to know if this message came from Alice, Alice can encrypt with her private key, and you use her public key to verify, by decryption, that it was Alice who sent it, all right? Now, one of the most important things about public key cryptography is digital signature. So the idea is we've got a big document, and we want to attach a signature. So there's two things. You must make sure that the signature is attached to the unmodified document, right? So you take a hash of the document, and then you encrypt it with the private key, right? That's called a digital signature. So you send a message with a digital signature. On the receiving side, you use the public key to decrypt the message, you get the original hash value, right? You take the message, you calculate the new hash, and you see if the two hash values are the same. That tells you that the person who signed the message did sign it, and the message did not change. So that's a digital signature. Well, digital signatures are nice, but they're not enough without some public key infrastructure. Why? Because you must know that this public key came from the right person, Alice. What if an attacker, Eve, sent a public key and said, this is Alice's public key? How are you to know? So the idea is you use certificate authorities, which are like the DMV, Department of Motor Vehicles. The certificate authority must check that this is Alice and this is her public key, and then create a certificate of Alice's name with her public key and how long this certificate is valid, and sign it with the certificate authority's signature. So there can be chains of trust of certificate authorities, and certificates are defined with known formats, okay, like X509, and this is all called public key infrastructure, right? So you can use both public key and private key, public key and symmetric key, because the reason you want to use both is public key cryptography is maybe 3 orders of magnitude slower than symmetric key, all right? So you want to use public key crypto rarely. So what you could do is you use the public key cryptography to send the symmetric key, all right? By signing the symmetric key and targeting the encryption for the recipient. And then after that, the recipient and you can use this symmetric key for bulk encryption. This is often called the session key, the key that is valid for that session, all right? And so, to conclude, I want to mention that there's secure sockets layer, all right, which you all know, also called TLS. And this is used commonly to secure web transactions over the internet. And what it does is, first, there is the handshaking part. This is the authentication of both parties. Now, if it's Alice buying from Amazon, Alice wants to make sure this is a real Amazon. Amazon may not care if it's real Alice or not, as long as she pays up with the correct credit card information. And so you have this authentication up front using public key crypto and exchanging the symmetric key that you will use for the session. That's called the handshake part of SSL. Then later on, in the lower half of this figure, you will do the hash generation for the message to make sure the message doesn't change, and then you encrypt the whole thing, okay? So that's the session cryptography that you will use, called the SSL record. So I know I've gone through this very, very fast, all right? There is a book called Security Basics for Computer Architects. It's produced by Morgan Claypool, and it's just about under 100 pages of text, so I think you could read it on 1 or 2 cross-country plane flights, right? But it gives you maybe 10 times as much information as I've been able to present today. Morgan Claypool says that they will give you a 20% discount if you order this book and say you're from Hot Chips, right? They were actually going to bring copies of the book, but there was a little mix-up, and so you can get this book if you want, and it will give you a bit more information, okay? And that's this part for security basics. Thank you. Okay, so next I would like to introduce Vikas Chandra. He is a principal engineer in corporate R&D at ARM, and he received his PhD in EE from Carnegie Mellon University in 2004. So he has written a lot of publications and has invented 15 patents and is associate editor for TCAS. He's also won ACM SIGDA Technical Leadership Award and is a senior member of IEEE. So he would talk to us about ARM Trust Zone and other issues.
Thank you, Professor Lee, for the introduction. It's my pleasure to be here to discuss mobile hardware security. It's an area which I find quite fascinating. This talk was supposed to be given by Rob Aiken, who could not be here due to a last-minute conflict. So I'm here filling in for him. Hopefully he'll do a good job as well. So this is the outline of my talk. I'll start with the mobile security background. After that, the bulk of the talk will be related to the trusted execution environment, and ARM's Trust Zone is a specific implementation of that. Towards the latter part of the talk, I'll discuss the implementation and use cases, briefly touch upon authentication, and then conclude. About ARM. We are a tiny company based out of Cambridge. But apart from all the staggering number which you see on this slide, the important thing to note is that ARM is an IP company. So if you have to count the number of chips that ARM has shipped out, it's exactly 0, because we don't actually design and ship silicon. What we design is IP, and work with our partner companies to make sure that all those ideas get translated into products and get shipped in volume. In this particular example, as you can see, a mobile hardware has lots and lots of components. In this particular talk, I'm going to discuss mostly an apps processor or application processor and how we build security inside that in terms of trust zone and whatever features along with it. So since this is a talk on hardware security in mobile area, let's try to understand what are the different threat environment in mobile. So since smartphone or tablet have become common nowadays over the last 6-8 years, there are different increasing risks, specifically coming from different apps which could be installed on your device. So there could be Trojans running on your social engineering app, which could ultimately do phishing, or it could also be advanced persistent threat, etc. There could be malware installed as a separate app in its entirety on your device, and that could be snooping on your private data, which is stored, and maybe sending it to a rogue server somewhere. Many times there are physical loss or theft leading to risk to data, calendar, your email, your photographs, etc. And in many cases, we have seen that a lot of people still don't secure their device with passwords or PIN. And if they get lost, then it's much, much easier for someone to just take the data off the device. Lately, there's also a new trend of jailbreaking. So you can take your actual OS installed on the device, and you can go and modify that so that you can have more control on your device. It has some good features and bad features. The good feature is that you actually have more control. The bad feature is that if you don't know what you're doing, then you are opening yourself to a lot of malware and other snooping apps. In addition, I'll talk about this a little bit more in detail in coming slides, but mobile has also become the enterprise security boundary. So a lot of companies are now allowing employees to bring their own tablets, smartphone in workplaces, and at that point, it becomes very, very critical to separate the two domains where your enterprise apps and data can live separately on your device as opposed to your personal apps and data and so on. So the bigger issue is that we need to design security as a system-wide security and not just add on extra layers of security to whatever we have. Everything needs to be thought from ground up, and that is the crucial thing which I'll discuss in this particular talk. So since I mentioned that data is important on a device, let's try to understand whose data is involved. So first of all, if you are the user of a mobile or tablet, it has your own data. So it has your personal information, it has your contacts, location, email, photographs, where you have visited over the last years or few years, etc. If you take your device to your company where you work, it could have enterprise data. So your company might install their own set of apps. In some cases, they have an operating system. So it has those kind of data as well. It has data from a carrier. So if you have AT&T or Verizon, whoever, they have their own set of software running on your device to authenticate when it communicates with the cell tower, etc. So it has carrier data as well. In addition, there is a huge range of applications which are actually running on your device. For example, if you are watching Netflix, if you're watching a digital rights managed video, so it has enough software for it to decode and unencrypt so that you can watch the movie or listen to the songs. In addition, now we have banking software, we have credit card apps, all that is also running, and they have sensitive data as well. In addition, with the new introduction of this whole IoT-based automation, you could have your home automation, your health, a lot of that kind of what we call little data, which can live on your device, and that needs to be protected as well. So given that we understand that data is critical, let's try to understand what are the security profile for different kind of attack situation. So on this chart, on the y-axis is the effort to attack a system, and on the x-axis is the effort to secure a system. The first blob on the bottom left is what we call a hack attack. It's essentially a software attack, and you can think of some teenagers sitting in some random country who is able to do that over software. Essentially, it consists of malware, installing malware and virus on your device, and it could also come through social engineering apps where you have accidentally signed onto certain apps and you have given permissions for that app to look at your social engineering contacts, data, pictures, location, etc. The second one is what we call shack attack. So this consists of non-invasive hardware attacks. And essentially, this is all about side channels. So differential EM analysis, differential power analysis. In some cases, if someone has access to physical access to a device, you can also do JTAG, bus probing, look at I/O pins, and try to figure out what kind of things are happening inside the chips, and then break down to get whatever information you want to get. The third one, and the toughest one, is what we call lab attack. And in this situation, it's really an invasive hardware attack. And it's done by someone who is well-resourced, has a lot of money and time. And it's a kind of attack which is difficult to protect against, and there are some solutions out there. So in this particular talk, the technology which I'm going to discuss, TrustZone, which is ARM implementation of the trusted execution environment, essentially is to protect against the bottom two, the hack attack and the shack attack. For the lab attack, there are solutions which I'm not going to be covering in this particular talk, and essentially they are there as a secure core, which are implemented in things like smart cards or high security modules or NFC in your phone if you're using your phone as a wallet, etc. Now, one thing to understand is that mobile solution is not really a PC solution. So in the PC world, there are lots of, because when PC came along, security was not the primary concern, but over time, security was actually added on as a solution. So we now have single sign-on, we have key fobs, we have two-factor authentication, all that kind of extra layers which we have added to the PC domain doesn't necessarily translate directly to the mobile world. The reason being that a lot of those solutions are actually unwieldy and confusing, and in many cases, the users of your tablet, mobile phones, smartphones are not very tech savvy, even in the developed countries as well as the countries where the growth is actually very, very explosive. So it's very, very important that whatever security solution we actually put in our system needs to be very intrinsic. It needs to be built in the device and the software itself, that a lot of what you do is very, very abstract. So a lot of what you do, the security in those areas is actually abstracted out of your own settings, for example. So we don't want the users to enter multiple passwords and then get a two-factor from another website and so on. It needs to be built in, and that's very, very important. So what are the different components of mobile security? One important thing which we need for that is a hypervisor. Hypervisor is nothing but it's a virtual machine monitor, which separates large pieces of code. Essentially, it allows you to run different operating system on the same piece of hardware, and that's a very, very important component of a mobile secure system. In addition, we need a trusted execution environment inside application processor to isolate your non-secure side and your secure side. On the non-secure side, you could have applications which are your normal applications, which doesn't require a specific security aspect. And on the secure side, you could have applications which actually are very, very critical and which have sensitive data. And the last one is secure element for tamper-proof, and this is for the situation which I discussed in the last slide, the lab attack situation. For those cases, there are secure core solutions for tamper-proofing those. In this talk, I'm not going to discuss a lot about the hypervisor, but the talk is mostly going to revolve around the trusted execution environment, how does it work, what does it entail, and so on. So, what exactly is a trusted execution environment, and what does it do? Okay. First of all, for any hardware security solution, there has to be a root of trust in your hardware. It cannot be in software. And that could be as a chip ID, which is authenticated, and it basically lives somewhere in your hardware. It could be a PUF, or a physical unclonable function, where you have a challenge response pair to help you verify the authenticity of your device. It has to have a secure boot, so that when your device boots up, it boots up in a secure mode. In addition, it needs to have secure peripheral access. So your screen, keypad, fingerprint sensor, etc. needs to also be in a secure mode, so that a rogue application cannot take access or snoop on that. You also need to have secure application execution so that if an app needs to run in secure mode, then it can. And that's a key feature of this one, of trusted execution platform. The last thing is that you need to have trust, which needs to be established, not only your normal world or non-secure applications on the same device. It also needs to have trust with internet or cloud apps so that if it's communicating, let's say, a financial transaction, then that particular transaction needs to be trusted as well. Let's take an analogy of a castle to understand how all this works. Since we're a British company, it's kind of appropriate to use example of Tower of London. If you look at this picture, what you see is there are lots of layers of defense. You start with a big wide moat at the very end, at the very periphery of the castle. Then you have multiple layers of walls. So instead of one big wall, it's actually broken down into multiple layers so that even if you can go over one of the defense, you still have multiple ones to go through before you reach something which is very well protected. The whole idea is to create your defense in layers and to reduce the attack surface. And it leads to two important principles, is isolation and the least privilege, that one needs to have access to a particular piece of either jewels or software or particular peripheral, if only it needs to have, not only because it wants to. However, a modern OS/framework is multi-tens of gigabytes. It's not just a small piece of software. In addition, on your device, there are huge number of apps running which could still go in gigabytes range. So maybe we should think of this whole concept as a walled city and a castle, where your castle is the small one shown in the right blue corner, where you have actually kept your crown jewels, but everything else is like a walled city where all your normal world applications live. Now, attacks will happen, and they have happened in the past, because everyone knows where your key assets are. The interesting story is that in the 17th century, someone actually was able to get inside the castle by bribing the guards. So even though if you have all this interesting moats and walls and all the security, you can still get through security by breaking your weakest link. The other interesting aspect was that a few years ago in 2012, there were some people who actually managed to steal the key of one of the doors, and they were able to break through inside the castle. And many of the guards actually could see them on their screen, but the protocol for them was not to leave their own particular areas where they were working, and so they were able to get through much inside before the police came and grabbed them. So the important thing to note is implementation details matter a lot. So even if you build a system which have lots of security in it, you have to understand all the protocols and how they all interact together to ensure that your system is actually stable and robust and secure. So a few more slides on this castle analogy, and then I'll move away. So trust zone technology actually creates a much smaller security boundary with just one door for entry and exit. So in this case, you can see that I've shown an example of the Golden Gate Bridge as basically carefully designed one entry, one exit out of your secure small castle where your really, really trusted data lives. And it's very, very difficult to get access to that particular piece of, well, in this case, a castle, but in reality, in hardware. Now, keys are only used in secure world. So there is protected crypto, there is encrypted storage, there is secure execution, and secure peripherals, etc., as a part of this secure world shown on the top right. What it offers is, as a part of trusted boot, it offers confidentiality. But the most interesting aspect is that for most normal world, that part of the secure domain is not even visible, which is a very important aspect of security. Just to give an example of what kind of softwares enable you to do that. So for the secure world, there is a trusted OS, which is an example of that is Trustonic T-Base 300. And for the APIs to communicate between the non-secure world and secure world, one example is a global platform client API, which essentially works with a secure monitor call at exception level 3. More on exceptions will come in later few slides. So essentially, trust zone, you can think of very simplistically as two CPUs virtualized in one. Now, in the pre-trust zone systems, there were actually two separate CPUs running non-secure applications and secure applications. Now, what that does is basically it separates your hardware, which is good and clean from a system perspective, but it puts extra burden on your power, on your performance. The control logic becomes very, very complicated, and the silicon cost also goes up. And it's not really a very scalable solution to separate the two pieces of logic, when in many cases you're not using your hardware logic for a secure side very often. So the solution to that is to do virtualization. And the key advantage of doing this is that now you can actually share your CPU resources, and they are dynamically shared in time, depending on what execution is happening on your smartphone or your tablet. Now, this gives two domains in the same machine, as I mentioned earlier, your secure and non-secure domain. And sometimes we get asked about what kind of overhead does this entail to add on to a system. And the short answer is that it is very difficult to give precise value of the exact overhead, because a lot of the components are very, very tightly knit between the two worlds. And it's very difficult to separate them out and count what exactly is the overhead. That said, in the latter part of the presentation, I'll give some gate count of different trust zone blocks to understand what kind of numbers are we talking about. The key point is that we use exceptions to move between modes, and that's something which I'll discuss in the next few slides. So this is a very simplistic cartoon picture of a 64-bit exception level in ARM architecture. So on the left side, we have the non-secure world. And in this case, there is a hypervisor running, which could have two operating systems running on top of that. And you can think of one example where one of them is your personal operating system, and the other one is your enterprise operating system, so that you can actually access apps from your employer. And then all this is running under the auspices of Trust Zone Monitor. And on the right side, there is a secure OS and the secure set of apps which are running on top of that. So if there is an app in the non-secure world which requires access to the secure side, let's say a secure peripheral, let's say you are trying to buy something on the web and you need to enter your password, and so that it needs access to your keyboard, which is a secure peripheral. So the way it works is it will raise an exception, which will go to guest OS. It will further raise an exception, which will go to the hypervisor. And finally, at the Trust Zone Monitor, which is exception level 3, it will start to communicate with the secure world. And then the communication channel is set up, and the data is exchanged, and so on in a secure, encrypted manner. I have simplified this in great detail in this particular picture. However, there is a whole lot of understanding which needs to go in building this to ensure that the whole communication is done in a very seamless manner. I'm not going to go into detail on the stuff which is shown on this slide, but on the bottom of this slide, there is a reference to a couple of documents which actually describe a lot of that in great detail. One of them is the ARM Architectural Reference Manual, and other one is an architectural spec. And they describe in great detail how the exception levels work, what is done in case your application is the 32-bit versus 64-bit architecture, and so on. This slide just gives a brief idea that apart from the architectural registers of a 64-bit architecture, to enable this communication between secure and non-secure world, there are actually separate physical registers which exist for different exception levels, and they are also privileged so that access to them for both read and write is very well controlled. And more of that is also described in the link which I have on this slide, and you can read that in your leisure. So let's talk about the attack approach. What kind of attacks can, in theory, happen in a mobile system? So let's say if you have a client app, which is something which you have trusted, something which you have downloaded from a trusted source, and you know that it's basically something which is not snooping on your private data. So this client app, if it needs access to a secure peripheral, for example, can make a secure call to the trusted execution environment. However, this malicious app can, in theory, attack the OS or the kernel. Okay? I'm not saying that it's trivial to do that, but hypothetically, let's say it does that. If it does that, it can then access the memory used to communicate between the client app and the trusted app. Now, once it has that information, then the malicious app can actually intercept traffic. It can replace it, modify it, it can eavesdrop, it can collect the data, and maybe send it to a third-party server. The other scenario is a side channel attack. So if you assume that the communication between the non-secure and the secure world is actually something very privileged, that's a very wrong assumption, because in most cases, it's not very, very difficult to snoop on the communication channel itself. One example you can think of is, let's say there is a client app. Again, I'll give an example of a banking software where you are entering your keys on the secure peripheral. So the keyboard itself is secure, but it's possible that the malicious app is somehow snooping on which part of screen you are touching as just an XY coordinate, and that gives a side channel information in decoding what software someone is entering. So there is always a way to for the malicious app to get hold of the communication channel. And once it does that, then it can basically snoop, and it can maybe possibly make its own call to the trusted side of the operating system. So what kind of defenses do we have? So first of all, as I mentioned, your normal world to secure world communication are always exposed and vulnerable. Right? There is no doubt in that. So don't design system which rely on secure communication between the two worlds. And the way to do that is to go through the data encryption and decryption. So always rely on trustworthy components like your crypto library, protocols to ensure that whatever sort of encryption you're doing is robust and not easily broken. So one thing to understand is propagating system-wide security is not just the task of your execution unit. It has to be a system-wide effort. So in this particular example, what I'm showing is that your TLB is also aware of which bits are in secure world and which bits are not in secure world. It also is there in caches. It's there in the bus interface unit. It's there in your AXI or AMBA interconnect, which connects your slaves to the different components. So this whole approach of building a secure system is not just piecemeal approach, but it all has to come through a system-wide approach where every device or every block in your CPU is aware of security, and it's handled in a holistic approach to make sure that everything is secure. I did talk about the overheads a few slides ago. Here are some examples of what kind of gate counts we're talking about. So if you look at, and I have 3 examples in this particular slide. So trust zone address space controller typically is 10,000 to 100,000 gates. Again, this number is not very large for cases where we are talking about architecture which is few 100 million transistors. The internal memory wrapper and the protection controller are both very, very tiny, so they're on the order of thousands of gates. So not very large overhead. One other example I want to bring here is your application of the hypervisor for bring your own devices to work, for example. So even if you are not going through a secure world, hypervisor can actually allow you to isolate your personal apps versus your, for example, enterprise apps. And let's say if you need a communication between your personal apps and enterprise apps, that can still happen. It will still happen through the exception level architecture. But instead of going to exception level 3, you'll probably do that at exception level 1 or 2, where you go through your enterprise OS, you go through the hypervisor, the communication link can be extended between the two, and the data can be exchanged. So a hypervisor-based approach actually gives you more flexibility to even communicate between different guest operating system in your normal, in your non-secure domain, as opposed to just using it for secure and non-secure domain transactions. This is an example of what it takes to build a system, for example, and this particular example is for digital rights management. So let's say you download a premium content, your favorite movie, for which you have actually paid. So you have the digital right management to basically decrypt the movie, to send it to a video codec, and finally it goes to display and you can watch a movie. Now, Hollywood studios who have a lot of stake in this particular market are spending or are actually thinking a lot about how to make sure that at any point in this particular flow, from your premium content to display, nothing is actually stolen and sent off as basically a cloned movie. So there are a lot of solutions which actually gets to be done to make sure that that doesn't happen. So there are firmware which protect against tampering. Once the decryption is done, then you have the unencrypted content is actually protected. So whichever memory buffers it lives in, nobody else has access to that. So other apps cannot access to that part of the memory. And the same for display. So whatever graphics engine is actually doing the rendering, it also is ensured that the graphics memory is also well secured, and other apps are not able to access that particular piece of data. So this whole flow is done in very seamless manner so that you are running a very premium content, but the security is built in such a way that at any point in the whole flow, the data is not going outside of a device. This is an example of secure implementation again, but it brings in your graphics driver. In this case, it's a Mali example, which is an ARM graphics core, and your bus interconnects as well. The idea of implementing all this together is that it gets you low cost and complexity. It leads to minimal memory fragmentation, and it also increases your flexibility and protection. So one thing to understand is that there is a hierarchy of trust, starting from your rich domain, protected domain, trusted domain, and secure domain. In this case, we have mostly talked about protected and trusted domain, which are in the auspices of trust zone or trusted execution environment. The secure domain is something which I have not covered, and that's a topic on its own. So this is a bit of an eye chart, but let's try to understand. So any application which is run on a typical mobile device has implications for all this hierarchy of trust, which was mentioned on the last slide. So for example, if you take a vertical segment, let's say a mobile payment, you can see that typically an application which is running, let's say a banking software, which could start to run on a normal operating system, but over the course of how you are accessing, it will actually go through protected, trusted, and in some cases maybe even secure domain if it's an NFC or a wallet or something which you're using it to pay from your phone. So there is a vertical segment where very clean hands-off happen as you go through the execution of your application in your secure and non-secure world. And there's an example in the next slide. So let's say if you are on a merchant site on your smartphone and you're trying to buy something. At some point, you'll be prompted to enter your PIN for your bank account or your credit card and so on. And at that point, the rich OS hands over the application to the secure OS. And at that point, the secure OS can call the secure peripheral, in this case the keyboard, for the user to enter the PIN. And after that is done, the data can be encrypted, and the control is then sent back to the rich OS, which can then send that data to the server, and then the transaction can take place. So this is a very clear example of how a particular application which is running on the non-secure side sends and handles data going from non-secure to secure and vice versa. I mostly talked about the trust zone-based ARM which is implemented in the ARM system, but there are a lot of interesting white papers out there which I think you should go through. There is one from Apple, Samsung, and Microsoft in this particular example, and they give a lot of interesting overview of how each of the security components are built in their own system. Now, there are different security recommendations from the security group. CESG is a UK-based group, and they have different security requirements, which one has to go and make sure that your system complies with all of that. I'm not going to go through all of that in great detail, but let's take a few examples to ensure how we meet them. So the first one is assured data at rest. So this means that your data at rest should be suitably encrypted. And typically, ARM SoC has a crypto hardware engine to decrypt and encrypt files. And there is also now crypto extensions in the 64-bit architecture. So there are specific instructions which are now actually added to the 64-bit architecture, the V8 architecture. The hardware unique key is only available to the trusted OS, and which is fused in silicon, and that actually is used to derive other keys. So there is a root of trust which exists there. Key material can actually be kept on the secure world side or encrypted and wrapped and stored as metadata, and so on. The second aspect is the assured data in transit. So IPsec is a way to encrypt and authenticate every packet which is transmitted from a device to outside world. So IPsec VPN is assured foundation grade, and that is basically also implemented in the trust zone system to secure your data in transit. The last two aspects which I'll discuss in this context are authentication and secure boot. Authentication is something which I'll actually go a little bit more in detail in the next few slides, but it's essentially user to device, user to service, device to service, etc. And we need to ensure that whatever authentication protocol we have is consistent so that different things can talk to each other in a very clear and concise manner. Protocols such as FIDO, which stands for Fast Identity Online, will simplify this silo nature of authentication status quo, and I'll discuss FIDO in more detail. Secure boot is another aspect which ensures that when your device boots up, it actually boots up in the secure side, and after everything is verified to ensure that the device is actually authentic, then the normal or rich OS apps get access to different components of a system. So why do we need authentication? Well, it's very interesting, and Professor Lee touched upon that briefly in the last presentation. People use the same simple passwords all the time, right? There was a study done where someone analyzed 6 million accounts and showed that the 10,000 common password would give access to 98.8% of all the accounts. That's really staggering number. And people do reuse them very, very often. So in a few years ago, there was a study done where people had 25 accounts and used only 6.5 passwords on an average. So the reuse is very, very common. And in terms of when people are trying to access financial or credit card companies through their smartphone or tablet, then having them to enter this unsecured passwords is quite risky. And that's where the FIDO protocol comes into the picture. So what exactly is FIDO? FIDO is a way to build authentication on your chip so that when you communicate to the external world, there is a level of trust built in on the communication coming from your smartphone or tablet. So it goes through this thing of registration where you have to register your device, authentication, and then transaction confirmation. Again, this could be on two levels. It could have complete passwordless experience, and you could use your biometrics. So for example, fingerprints, your voice, even retina, because your smartphone has cameras. And then that could be mapped onto a very small authenticator format, and that can be shipped off to the third party. And I'll discuss more in detail on that. And there could also be a two-factor authentication where, in addition to a password, it can also sense your fingerprint sensor, and it can authenticate that particular transaction. So what FIDO Authenticator does, it takes, as I mentioned, the biometric, let's say your voice, your fingerprint, your password. It encrypts that into a encrypted data, and that goes to a FIDO server. And this works very, very easily, very, very cleanly on the concept of public and private key cryptography or asymmetric key cryptography. An example is shown here. So on the user side, there is a FIDO client which lives on your device, and it actually takes your password or biometric, and using a private key, it encrypts that particular piece of biometric or password or whatever input you gave it to it. And then there is a protocol. Whenever you're doing a transaction to a web application, for example, in this case, you transfer that encrypted data, and that is decrypted by the FIDO server using a public key stored on the server. And then it communicates with the web application you're trying to, let's say you're buying something online or your financial institution, and that's how the framework works. Now, this particular circle, which is on the bottom left, is actually quite ideal for trust zone-based implementation because the private keys can live very, very nicely in a secure world. And whenever someone is entering a password or a biometric, that transaction can be handed over very, very cleanly to the secure side, and authentication and encryption can all take place, and the encrypted data can be sent back to the non-secure world, and then that's transmitted to the server side where the FIDO server verifies the authenticity, communicates to the website, and the transaction can take place. So it's a very good example of how FIDO Authenticator and Trust Zone can live together. So this brings to end of my talk. The most important thing to understand is that mobile security is actually built on hardware root of trust. Having said that, it does require your hardware and software and security and security services to work together in a cohesive manner for one to have a device which is secure and the data is not lost easily. FIDO is one example which now people are putting on the device to ensure that the authentication, etc., can happen in a seamless manner without entering a lot of passwords and so on. And that will bring us much closer to a very, very seamless experience of using a secure, using your handset or mobile for application like banking, etc. So that brings me to the end of my talk. And after the talk, we have a session of Q&A where I'll be happy to answer more of your questions. Thank you.
So we're very happy now to introduce the next speaker, Dr. Leendert VanDoorn. He's a corporate fellow and corporate VP at AMD, and he's responsible for driving software innovation across the whole company. He talks frequently with AMD's software partners to understand their roadmaps and feeds this back to AMD. And he's also the evangelist for AMD's future plans with AMD partners. So Leendert is responsible for all of AMD's security, virtualization, manageability, and software ecosystem strategies. And he's been actively involved in AMD's ARM 64-bit server ecosystem enablement. He has been on the leadership team and participates actively in AMD's roadmap process. So before joining AMD, he was senior manager at IBM TJ Watson Research Center, where he did virtualization and system security and penetration and system usability with their research teams. He holds a PhD from Netherlands, and he is also an adjunct professor at CMU.
Thank you, Ruby. So originally, the organizing team had asked me to talk about game console security. Unfortunately, I cannot talk about that. That's obviously covered by NDAs. What I can do, however, is talk about a lot of the basic principles. And that's what I'll do. And I'll use a lot of examples from projects I've worked on in the past to illustrate these concepts. Also, in this talk, I'm going to focus on two main concepts. One is integrity. You've already heard Ruby talk a little bit about that. And the other one is isolation. So those are two of the key core concepts by which you build secure systems. So you can't open a newspaper without reading about some sort of security attack. Either lots of passwords are stolen, lots of credit cards are stolen, but something that is the most interesting thing to me over the last 15 years that I've been working in computer security is that security has gone from a nuisance that hackers did to actually something that is weaponized and is heavily used by criminals and nation states alike. So the examples on this slide here show you Stuxnet and Flame, allegedly used by the Israel, or designed by the Israeli and Americans to go after the Iranian nuclear enrichment program. But it also shows examples here of Project Aurora, which allegedly Chinese hackers broke into Google, Intel, and a whole bunch of other US companies. So, and then of course we have all the Snowden revelations that recently happened. So all these security things or attacks that security research is hypothesized about, all of a sudden turn to be right and turn to be actually used by people. Now, of course, if you think this is just the US doing it to all the other states, let me give you an example. When I worked at IBM in 1999, I got a resume on my desk from someone in Russia. Now, the person wasn't really working on security, so it wasn't really relevant. But the reason why the recruiter sent it to me is because during his civil service in 1984, he had been working for the Red Army doing computer viruses that interfered with the MFM encoding of a hard disk. So it's not just the US doing it, every country is doing it, and it really has become weaponized right now. So let me talk a little bit about secure systems. So I have an operational definition of a secure system, and it's a system that behaves as specified and nothing less and nothing more. Now, the first thing you'll probably notice is there's no reference of security in here. And there's a reason for that. Of course, technologies like crypto and access control lists and capabilities, they're all part of a secure system. But they by themselves do not make a secure system. To give you an example, you can have the best crypto algorithm in the world in your system, but if your random number is flawed, which is used to actually generate all the secret keys, you're completely toast. And that actually is quite often where the weaknesses are. Why does the US government allow strong crypto to be used? Remember back in the 70s and 80s, they had all these stringent rules in place that you couldn't use certain crypto algorithms. They relinquished or released all of that in the 1990s, the late 1990s. Why? Because it was quite often much easier to get to the clear text, to get to the unencrypted text, way before it was encrypted. So that's where a lot of weaknesses are. And in fact, one of the Edward Snowden releases actually talks about generating poor keys. So that's why it's way more complicated than that. So it's also secure systems. If you look at this definition, there is a bunch of other problems with it as well. First of all, we typically don't specify our systems very clearly or very well. So there's a lack of specifications or lack of completeness of specifications. The other one that's really difficult to do is to prove that there is more functionality in your design or in the actual implementation than was specified. So let me give you an example that DARPA has been very concerned about. Imagine that you're building yourself a cruise missile, and that is a pattern recognition chip that recognizes maps in order to identify the goal. And imagine that this chip is produced in Taiwan, and there is some code in there that says, well, if this looks like Taipei, we're not going to work, right? We're basically going to give back another result of another city. How do you prove the absence of that? Frankly, it's really hard. So there's a whole lot of issues around that. So secure system designs, and Ruby alluded to that as well, is a cost trade-off. Like any engineering project, you can make a highly secure system. For example, at IBM, I was building physically secure coprocessors, where we set the target as like, that takes you about $1 million to break it. As a result, this device cost you about between $12,000 and $20,000. Was this a PC, something applicable for the PC market? No, absolutely not. It wasn't a PCI Express slot. You can put it in a PC, but that was not the target market, right? So you really need to trade off is like, what's the value we're protecting? What's the cost that we're willing to carry for that versus then the security you get for that? And systems will be broken, right? So you also have to very clearly identify who is your attacker, what are you defending against? And that goes to some of the threat analysis that Ruby spoke about. So critical to secure system designs are well-defined security properties. What are you trying to define? What are your objectives? What are you trying to achieve? The threat analysis, who is going to be your attacker? How much money are they going to spend on it? You obviously want to, if you have these scenarios, like for example, the example I just gave for the physical secure coprocessor, we knew it could be broken. It cost you about $1 million, but we made it such that you only could break that particular device. So the only keys, the only secrets you got, and the only thing you were able to emulate was that particular device. You would have to spend another $1 million in order to break a second device, and so on. So those kinds of properties are very important. And then, of course, design methodologies. You have to have proper test plans, penetration plans, code review, all those kinds of things that make the project costly. You all need to have that in place. So what happens if you don't? And I just want to give you these examples because they're sort of illustrative of the kind of attacks that attackers use. So this is an example of a code injection attack. So stacks grow downward on an x86, actually on most machines that I'm familiar with. Whenever time you call a function, you've got a caller activation record. Underneath it, you've got your local variables that are on the stack. And then, of course, if you call another function, the whole process repeats again. So now, take the following kind of simple C code. You could imagine that this is the main input loop of the web server, for example. You have a buffer on your stack, you read input from something, and this happens to work. You read the input into a buffer. The buffer obviously resides on the stack. It's an automatic variable in this case. And if you just read input 0 to 10, everything works fine. Right? The function will do whatever it's supposed to do, return, everything is happy, nothing is compromised. Now imagine giving it a much longer string, way beyond the 128 or the 20 characters in that buffer. That will overwrite the buffer. And what will it overwrite? Well, it will write up in memory, so it will overwrite the caller activation frame. So obviously, if this function returns, it will actually crash the program, and it has to be restarted. Now, as an attacker, you can actually take advantage of this. So you basically write the first 20 bytes of garbage, then you know where you end up in the caller stack frame, and what you then write is actually a fake return address. And what do you do with this fake return address? Well, you point it to code that afterwards you put on there. And this is how you can break into a web server, get a shell running, and actually then get into the system. Now, obviously, people have gotten smart. They've come up with non-executable shells or non-executable stacks. So people have found things like what they call return-oriented programming. So you basically, instead of putting code in there, you basically put a function in there or an address in there that points to an existing function, and you just make sure that it gets the right arguments. Say, for example, the system function, and you execute a shell. And there's plenty of that code around in a typical program. So there are many other tricks, and of course it becomes a rat race that people start doing random address space layouts and stuff like that. But there are many ways to actually get into a system like that. Now, before you all think that this is all these attacks are software problems, and yes, most of them are. Here's an example thinking about side channel analysis, side channel attacks. So every processor emanates side signals. So the one here actually refers to power analysis. It turns out that when you actually look at the power fluctuation of a processor, there's a lot of noise and a lot of signals actually in it. So if you then correlate that with algorithms, for example, in this case at the bottom, it's a DES algorithm. It's sort of the traditional example that people have been doing since the 90s, where they basically looked at power fluctuations while it was doing a DES computation. So you clearly see 16 rounds of DES. DES is a fairly regular, it's an old crypto algorithm. Nobody is supposed to be using anymore, but it has a very regular structure. And Ruby just showed you the AES algorithm, which is the latest crypto symmetric key algorithm. It's also a Feistel cipher, so it has a very regular structure, and it shows up as similar kind of things. Now, the interesting thing about this algorithm is that the first part, this here, actually, I was told I have another pointer, this one here. So this part, oh, I guess not. So the first part that you see in front of these regular 16 rounds is actually a key schedule computation. And if you zoom in on that, you can literally read out This bit of the key is 0, this bit of the key is 1, and so on. Now, this is taking it into the power domain. There are many other domains that you can take it to. People have been doing this with CRT screens, where they basically look at the ground cable, anywhere where there is inductive coupling going on. Great way of losing information. Or did you realize that if you take a conditional jump or not, it has a different radio frequency pattern? And so if you plot that out over a time axis, you can actually learn a lot of interesting information. So this is a very, very rich area of attack and a very difficult one to defend against. So it's not just software. Hardware has its challenges too. So what I want to talk about here is basically two main concepts, integrity and isolation. So integrity, to me, is sort of like, my definition of it is it ensures that you get the specified behavior out of the system. Isolation is when things eventually will go wrong. How do you contain it? How do you make sure it doesn't get out of its bounding box? The other benefit, of course, of isolation also means is you now have much smaller units that you can reason about, and you can think about, and you can make deductions about. So then there are many parts of this. Integrity, and I'll go into a little bit more detail about this, secure boot, code signing, access control lists, their counterpart capabilities, crypto accelerators, embedded things into hardware, separation of responsibility, least privilege, all those kinds of things are part of that. On the isolation side, minimal trusted computing base. So basically, and that was part of what the ARM talk was about, the TE is about that. Right? What do you want in your TE? You want only those functions in there that are necessary to protect whatever key material you have in there and nothing more. So minimize that trusted computing base. And I'll talk a little bit about I/O and CPU virtualization, dedicated coprocessors. There's a lot of exciting work going on around enclaves and memory encryption that you're finding back into a whole range of applications. And then hardware tamper resistant is a thing that we'll talk about a little bit too. So in the interest of continuity, I too have a picture of the Tower of London. So as was already said in the ARM talk, the integrity of your system, security of your system, needs to be grounded in hardware. We have seen this over and over again. Remember all those virus wars that we had going on, and this was a rat race? So back in the 90s, people started doing viruses, attacked applications. So what do? Well, you have a virus scanner that basically checks for signatures. Then they went after the kernel. The problem was that the virus scanner ran as an application, and of course, when you got into your operating system, you could disable that application and the game was over. So virus scanners needed to get into the kernel. The next thing that happened was that viruses got into your master boot record, which is a problem because obviously they could change the kernel to their heart's content because the master boot record was responsible for loading the kernel. That has been solved, and guess what the viruses are now? They're in your BIOS, right? So these are the advanced persistent threats that everybody is concerned about. And so you need to have an anchor in your system where you can start with. And typically what that is your first part of your system when you start running, typically your boot sector that sits in flash, that is read-only, or some read-only memory mask, that's ROM, that's part of your mask. That's where you start. That's where you typically embed some of your key keys there, you read your root public key, and that's how you then use to bootstrap the rest of the system. If you don't have that, if there isn't a mutable place in your system, you basically are toast, right? There is going to be, you open yourself for a rat race where anybody can get in before that, where you do critical checking. Now, there are many ways to ensure it, right? So a ROM in a mask is one of them. You can think about putting things in OTP, one-time programmable memory fuses. There's many, many ways to do it, but you need to have that standpoint. So one way to do it is through a separate security processor, and I'll talk a little bit about that. But then, of course, you've got a recursive problem because, yeah, if you take your main processor and you guarantee integrate or immutable root through a separate processor, then how do you guarantee that for that separate processor? So let me give you an example of a secure boot. So this goes back to really Bill Arbaugh in the, I think in 1969 was his IEEE paper. And it actually goes back earlier than that. In the 70s, there were a bunch of military devices, communication devices, that actually use similar kind of notions. So once you've got that immutable root, secure boot is actually fairly straightforward. What you do, right, before you execute the next piece of code, you basically do a digital signature check of it. And when that signature check succeeds, you go on to the next part, and so on and so on. So you basically extend that notion, right, of knowing in what configuration what state you're in, up to the next level. And it's really important that you obviously don't execute the code that's in the next level because you've verified that it's okay, that this code can be trusted. So secure boot has the nice property that if that signature check fails, it stops. You go to a recovery mechanism, which typically means reloading whatever bootstrap loader got compromised. And the other thing, of course, you do is you extend this all the way up in the operating system. So Microsoft Windows actually does that today. UEFI is the firmware that's being used on most PCs today. That's all securely signed. That's carried all the way up into the operating system. Now, there's a whole bunch of challenges with this, right? You need to have a place to store those secure keys. Trust zone is one mechanism. There are other mechanisms to do this. You need to figure out how to deal with rollback. Because, for example, you may have a firmware on there that is secure, but in the previous one you had a bug, and it's a known bug, but it's a properly signed firmware update. What prevents an attacker from first rolling back to the one with the bug and inserting themselves in there? You need to think about revocation of keys. Occasionally keys get stolen. How do you revoke them? Especially when you've got millions and millions of devices out there. Attestation is a notion of actually proving to a third party that you actually that you did boot securely and that you got into this state. And then there's a whole issue around key management. The other way that people have been doing this is called, is something that the Trusted Computing Group has been promoting. And this started in the late 1990s. First it was called TCPA, then moved into TCG. And what that is basically a passive storage chip. They call it the Trusted Platform Module. What it is a passive storage chip. You can write memory, you can write data into it. You cannot take data out of it. It basically collects a summary of that data. And when it gives you the data back, it's actually signed with a key that's embedded in that device. So that will actually lead back to this device that actually do that signing. And you can create some interesting frameworks around this, but the challenge with it is you always need a third party to tell you whether you got into a secure state or not. So let me talk a little bit more about that. So the functions that the TPM has is, it has this notion of program configuration registers, and it has about, I think it has 20 of them now. And it has a bunch of operations on it, but the key ones are extend. So you take whatever previous value is there, you do a bitwise concatenation of some sort of hash value that you put in there, and the hash value obviously represents a summary over the data that you're trying to hash here. And the thing, of course, it's a secure hash function, so that means it's computational and feasible to inverse it. And that's what you then apply a different hash function over, and that's the new PCR. So the result of this is that you can write a data into it, but you can never take it out because that F function, that hash function, is computational and feasible to inverse. You can do then a quote operation on it, which basically is you ask back the content of this value, and that's how you can then, and it's signed with an attestation identity key, and that's how you prove to a third party, yes, I really got into this state. It has then a bunch of other operations, seal storage. You can actually say, well, when I get into this particular state, then I have access to the secrets, and if I don't get into that state, then I don't. Of course, it has some non-volatile memory and all of that. So let me go into how this is actually used, and I'm sorry for using white on black there. So again, this starts with an immutable root. Right? So it knows the configuration that the system starts in. You know exactly that you are in code that has not been compromised. From that, you basically do this extend operation, right? So remember, you compute the hash over that next block of memory that you're going to jump into. Then you give that to the TPM, which extends it with whatever value is already there. The initialization values are 0. And then it will take that bitwise concatenation and take the hash of that, and that becomes a new PCR. And you can extend this all the way through, even up into the operating system. Now, if you're wondering, this is a build slide, I think. It's building a little bit less than I... Oh. Okay. So what it's doing, since it has a number of these PCRs, there is a standard that actually says the following parts of the systems need to go in this PCR, the following parts of the system need to go down in the PCR. There's some gaps because there's some history around some of these things. But what you can do is you can give this whole bag of PCRs to a third party, the verifier, and you can say, well, tell me, right, whether this entity, so for example, I'm a computer, a client is talking to a web server. I asked the web server to attest itself that it actually got into the secure state. It sends me back basically this attestation data that's stored in the TPM, so all these different blobs. I can now go to a third party and say, do you agree that this thing is in fact in a trusted state? And if it is, then I can continue to interact with it knowing that it has not been compromised. The key principle here, same as with secure boot, is you measure before you load. Okay, now, before you think that the only thing in an SoC is the CPU core, and therefore that's the only thing that runs code and therefore needs to be integrity protected, that is completely outdated. We've got, I think, more than a couple of dozens microcontrollers on modern SoCs. Right? So, and a lot of these microcontrollers are already starting to execute before the system is even running, before your cores are even up. And all of these microcontrollers have field upgradable code. Call it firmware, call it microcode, it's field upgradable. And these are all potential attack vectors. And so these all need to be integrity protected. So it's a key takeaway, because some operating system still assumes that they're the center of the universe, they're the only thing that's running, and they don't want anything underneath them. Well, that is gone. We've passed that bridge a long, long time ago. So it's one thing for the SoC or the system, the platform, to come up securely. The other part of it is then, okay, you've got all these keys. How do you manage these? How do you orchestrate that? So here is a very rough picture of what AMD's key distribution service looks like. We obviously have a centralized key distribution that's replicated. Every device gets its own unique key that we actually use for signing. So the key isn't available to users or to the kernels even to do any kind of identification, but we do use it to sign unique blobs for. Obviously, the service is replicated. There's obviously some complications where you have to inject these keys. The keys are typically injected, as I said, in fuses and OTP. This happens in FAPS, where you obviously need to ensure that this happens in a secure environment. You don't want people to get in there and insert their own keys. And then you have to deal with a lot of third-party requirements. We have customers that want to have their own keys in there. We obviously have to deal with consortia that do DRM kind of things that inject keys in this. And we have then debug. Because one of the things, of course, when you've got systems that have JTAG connectors on them, and you can basically read all the keys you want, that's not the right thing to do, obviously. That way you expose your systems. So the only way you can actually debug these systems is you actually need to get an unlock key from the key server, and that actually is a one-time key that only allows you to debug that particular system for a particular duration. So there are all these kinds of limitations around that. Things that you need to start thinking about when you think about secure systems design. So let me talk about the second part, isolation. So there's already been a number of references to virtualization. And there's going to be a few more in the next talk, so I'm not going to spend too much time on that, other than to say virtualization is a concept that goes back a long, long time. It's really about providing an illusion. And it's the illusion that you've got more resources available than in fact you have. And there is something underneath there that creates that illusion for you. In an operating system, we have that, and it's called virtual memory. Every process thinks its memory starts at 0. Obviously not the case, but you've got a memory management unit that's responsible for doing the mapping, and the operating system maintains that, and that's how that illusion is created. The same thing for virtualization. Underneath it, you've got a virtual machine monitor or a hypervisor that creates that illusion that you've got a complete system available to yourself with all the memory protection, all the bits and pieces that you find on a normal computer. Now, that allows you to create multiple virtual machines. And those you can use not just for drive-up utilization, like we have been doing. You can actually create service partitions where you do security functions. You can actually use it as a base isolation mechanism. And that's what we're seeing. The Intel speaker, David, is going to talk about DeepSafe, which uses these mechanisms. Obviously, you got companies like Bromium that are using it. And even Microsoft, in case you're not aware, every Windows 8 distribution actually ships with an embedded hypervisor in there. So this is a very fruitful area of security isolation, and everybody has built hardware support for that. Both Intel, AMD, ARM, all of us actually, we do a pretty decent job of that nowadays. The other part of that is I/O virtualization. So it's one thing to virtualize the CPU, another thing is to virtualize the I/O buses. And here the same principles are applied. So instead of saying whatever sits on the I/O bus are physical addresses, you basically virtualize it. Right? You make them I/O virtual addresses, and you put an I/O MMU in between that actually remaps these things. Now, in the x86 space, we obviously have PCI Express, so we can use the bus device function numbers, identifiers for that, and figure out what the right tables are and map it to the right place. In the ARM world, it's a little bit more complicated, but they have a system MMU that pretty much does the same kind of thing on a per-device notion. So this is interesting because it not only allows you to directly associate devices with virtual machines, it also allows you to cordon off what a device can do. So there's been a whole bunch of discussions about USB attacks or FireWire attacks, right, or DisplayPort attacks, where these devices can basically do a busmaster DMA, read everything in memory. Well, the I/O MMU allows you actually to reduce the amount of memory or the address space where these devices can access, and therefore you can cordon off what they can do to the system. So at AMD, we actually took a slightly different view of how we implemented security. We actually put a separate security coprocessor in place. We actually did it on ARM, so hence the trusted execution picture here, the trust zone picture here. But the reason why we did it was because it allowed us to tap into an ecosystem that existed. We also felt very strongly that we didn't want to sit on the same processor because there's all these side channels that I talked about, and one of the side channels that I didn't mention is cache effects. Everywhere basically where you've got a shared resource, right, that is used by two mutually distrusting entities, there is a communication channel. And so you want to reduce those. And the easiest thing to reduce this is actually to take it out. And that's what we did here. So that is what our notion is of the platform security processor. As I said, it's a separate processor. It runs independently. It's actually the highest authority in our SoC. So it is responsible for booting up the x86 complex, as well as enforcing the integrity checks, or at least the initial integrity check for the x86 cores, the AMD 64 cores, and from there on, then typically firmware takes that on. One of the nice things that Trust Zone gives us is that it allows us to do late binding. So we can actually load security functions in this processor very late on, even after things have already shipped to the customer. It also allows us to tailor the functions to the application domain of the device. So for example, in clients, things that we're interested in very much interested in are DRM kind of applications, of course anti-theft, those kinds of things. In the server space, it's more about key vaults, it's more about integrity of the system, specifically in the cloud. We're more concerned there about providing an HSM kind of functionality. HSM is a hardware security module. So again, crypto keys and those kinds of things. So that really is what this picture explains. There's a whole bunch of different use cases for the PSP. But that notion of having a late binding and being able to tailor them, that was very important to AMD. And around Trust Zone, there was already an ecosystem that we could actually embrace and integrate. So in the interest of time, I'm not going to dwell too much on this. Another area that's interesting, that has gotten a lot of attention, is attacks on memory. So there's a whole bunch of them. And I'm showing here a bunch of them, interestingly, all from Princeton, although I don't think that Ruby is involved with these particular projects. So what people have done here is do things like freeze memory, right? And if you do that and you actually insert the RAM in a different machine or you reboot it, the memory doesn't actually get erased. So it actually allows you to read that memory. There's a window that you can do that, but it allows you to read it. And that, of course, allows you then to look in this memory for keys. It turns out that keys have very specific mathematical properties, which makes it really easy to look for them. So that's one thing. The other attack that was actually from earlier in the 90s, where a clever student figured out that if he can generate a single bit error in memory, he can take over the security mechanism in Java. So Java is a popular language used on the web. Its claim to fame is that it's a safe language, it's a secure language. It has a fairly extensive security framework as well as a runtime environment around that to protect that. And so what this particular student showed is that he cleverly constructed his Java program, and he could create a single bit flip error. He could actually bypass that. And how did he create a single bit flip error? He basically put a lamp on top of memory, and he just waited for a little bit, and then memory heated up, single bit error started. Of course, that's resolved with ECC, but it gives you an example of what those challenges are. On top of that, you also have, and I already alluded to that, all those FireWire, DisplayPort, DMA, busmaster attacks on systems. So what's the answer to this? Well, you encrypt memory. You basically treat everything that is outside of the SoC as insecure. Now, this brings a whole bunch of challenges with it. One of them, of course, is you introduce latency. But that's one way to go after this. And that actually has a lot of interest. So there's a bunch of challenges with that too. So there's obviously, you need to think about memory modification attacks, you need to think about rollback attacks, you need to think about cut and paste attacks. Let me talk about that a little bit. So when you encrypt memory, it's not as straightforward as just all of memory is encrypted. Because one thing you can do is you can take actually memory blocks and start copying to different addresses. Right? And if you know what code is executing, you can actually create quite interesting attack out of this. So you need to somehow curry the address bits into whatever key you're going to use to encrypt those pieces of memory blocks for. The other one that actually is more challenging is rollback. So what prevents me from taking an older version of memory and overwriting the newer version that you're executing? Obviously, if I know that some sort of secure transaction is made, right, and I can replay that transaction by injecting the right encrypted pages or cache lines or whatever unit you pick into memory, you can bypass that. So you also need to have sort of a generation number. You need to have something that evolves with that. And that's actually one of the big challenges with encrypted memory. So there are good crypto algorithms for it right now. They're basically modes of counter modes. So the Galois counter mode is what I refer to here. It's an efficient mode where both integrity and confidentiality are one pass. So it's very efficient, but you still have to deal with where do you put your initialization factors. And typically, right? Since these are the key of the whole system that you base everything on, they have to be stored inside the SoC, so require lots of SRAM. So the typical solution to this problem is that you typically have pieces of memory that are both integrity protected and confidentiality protected. There are pieces that are just confidentiality protected. And then there are, of course, also pieces that are clear text, because whenever you communicate with devices, you obviously have to have a window to do that. So as I said, a lot of stuff is looking at this, and there's a lot of specific applications where this is already applied. So let me put it together. So this example slide here is absolutely dated. It's 2004. It refers to NSCUP, Microsoft Next Generation Secure Computing Base. The problem was that I couldn't find any more modern example, the examples that I know, I couldn't find any public information. Let me put it that way. So I'll just use this to hang things up. So all those technologies that we just talked about. So how are people applying those? Well, people are using virtualization to provide coarse-grained isolation. They're doing secure boot in order to make sure the system gets into a secure state. And typically what they do is they go up to the hypervisor, and depending on your system, they even let it go there, so they're just interested in the security of the hypervisor, that thing has not changed. So for example, if you go to your big cloud providers, that's one of their key concerns. And they just want to be able to know that if they're going to tell the system to jump, that it's really going to jump, and that it's their software that's jumping, to put it very bluntly. Other systems get more interested and push things up higher. So Microsoft definitely has a whole framework around attestation, right, where they're actually interested in taking this further. A lot of it goes back to these kinds of ideas. IOMMUs come into play. They're being used to cordon off devices. So only certain partitions can talk to the devices. Notion of service partitions, where partitions do particular functions. For example, do DRM management that ARM just talked about. That's a function. Now that function, that virtual machine, is then isolated by using all those isolation mechanisms, IOMMU, all those kinds of things, right, that it cannot be interfered with from other partitions. Then the other thing, if you take these kinds of applications into environments that are hostile, I mean, game consoles obviously being one of them, but the other thing you can think of it is cell phone towers, right, where traffic actually gets decrypted and gets re-encrypted before it is sent over, or transcoding is done on it, or any kind of other operation is done on it on the clear text. Those are obviously hostile environments. Visual secure coprocessors, they obviously live in an environment where people want to steal keys that are embedded in it. So there is where you get a lot of physical security capabilities. So that's one thing that I wanted to talk about, my last thing. This is something I worked on at IBM Research when I was there. This is was the first FIPS 140 level 4 validated physical secure coprocessor. So FIPS 140 is a industry standard, or is a NIST standard for the level of security devices that you have. So level 1 basically says that you have implemented your crypto algorithms correctly, but there is no physical security. Level 2 says, well, you need to be able to, if you unscrew the device, that you can see that you got in there. So there typically is dealt with microsensors and other kinds of things. Level 3 says, well, you can get into any opening. And level 4 says there's no way you can actually get into this device. And so that's both a hardware and a software story. So the key function of this device is to protect root keys of banks, right? So this thing is actually shipped in about 70% of all the mainframes, but also root keys of certificate authorities. I mean, if you've got a certificate authority like VeriSign and your key gets stolen, then you've got a big problem. And we actually saw that, right? We saw a bit, there was a Dutch certificate authority that actually lost their key got compromised, and they basically are not in business anymore. They don't exist. So you have to, in those kinds of cases, you also have to be concerned about insider threat. It's not just remote attacks, but it's insider threats, people taking off with the keys, and that's where these kind of devices come in. And we were fairly paranoid with building these devices. So for example, All of this is documented in a paper that's later on in this slide deck. The keys were stored in battery-backed RAM. There are batteries on these devices that could actually last for 5 years and keep the keys fresh. There was an analog circuitry in there to detect tamper. We didn't just detect that people got into the box, we also detected that people were doing X-rays. Because if you use a high X-ray source, you can actually lock the bits into place and you can open up the device and you can read it out. We were also concerned about rotating memory, because if you leave bits into memory for a long time, basically you get, name escapes me what the effect is, electromigration effects, and you can actually observe that under a microscope, electron microscope. So there were all these kinds of attacks that we were very, very paranoid about, as well as then we did an enormous amount of validation inside the device itself of the software stacks. We actually went through all sorts of, we didn't quite go for Comic-3, but we definitely had our eyes set on that. So here are some pictures of what we actually did. It's a general purpose computing environment inside a secure envelope. One of the interesting things with that is how do you take those wires out, and how do don't you create openings in there? How do you reduce the inductive coupling on that? So that's obviously a thing you want to prevent against. The other interesting thing is that people typically attack these things with acid. So the mesh that is surrounding it, you could basically think of its wires, basically a whole lot of wires around it, although they were in all sorts of different patterns that would overlap. And I think we had about 7 layers of them in different patterns. But the chemical makeup of it was such that if you try to etch away the resin, we actually used conductive ink, you also would erase away the conductive ink and therefore cause a break, and the device would trip. I remember seeing a picture from a test lab where they sent us the picture back, and it really looked like a porcupine that had been trying to stick needles in it, and it failed on every occasion. Anyway, sort of a nice sidestep of how to build secure systems. What I want to go over is there's a lot of attacks. The attacks are real. And as I said, the attacks are being weaponized, not just by not just by nation states, but also by criminal organizations. And we're reading about that every day. So software is still the easiest attack vector, but people are going to go to hardware. It's actually not that hard to break hardware. To give you an example, the side channel analysis attack that I did, I gave a special lecture at CMU where I actually had a device computing an elliptic curve crypto function, and I had a wideband receiver that was $350 that allowed me to figure out exactly what the secret key was of that elliptic curve crypto. So every grad student, or actually any student at any university, has all the equipment they need to break these kinds of devices. There are 2 building blocks to go against it. One is integrity, right? Make sure you know what you're executing and put all the controls in your system so you actually enforce that. The other one is isolation and containment, because eventually things will go wrong, and you'll have to have a mechanism in place to really contain what the damage is that these systems can do. It also allows you to reason about what you can do if the system is broken. Okay, with that, I conclude my talk, and I think we have a break now, right? So, all right, thank you. Thanks.
We're very pleased now to have David Durham from Intel. He's a senior principal engineer and director in Intel Labs. His research team developed anti-malware and cryptographic security features today in all those hundreds of millions of Intel processors. He also worked on policy-based network management technologies and created security solutions that are shipping in Intel vPro platforms. He also worked with McAfee to deliver virtualization-based anti-malware products. He collaborates with industry leaders and developed the 802.1 security protocols, as well as advanced network access control capabilities. He's also a prolific author on computer communications, has written a book and many publications and internet protocol standards. So he received 2 Intel Achievement Awards, has been granted over 100 US and international patents, and he got his BS and MS in computer engineering from RPI. So welcome, David.
Thank you, Ruby. So I'm going to spend time not so much repeating what you've heard in the previous talks, and I promise I do not have a slide with the Tower of London in it. I will not use that analogy in this talk. But I do want to get a little bit more under the covers of what the various software kind of attacks are doing, and basically from an agenda perspective, I want to make you paranoid if I'm successful, give you hope, make you paranoid again, and give you some more hope about where things are going in terms of computer, or at least processor architecture, to understand how we can deal with some of the emerging threats that, of course, continue to advance as we go forward. So starting off with the problem statement, you've heard of the popular ones before, and I think Leendert also described a few of these, like Operation Aurora. That's a good example of a targeted attack and advanced persistent threat that can get into corporate networks and start basically spying on activities there. Stuxnet, of course, you know, if you want to attack a nuclear facility, well, there's malware for that. You know, there's an attack for that. We've looked at things like these various spy software that listens and is on your microphone and probably turns on your camera covertly and can do these sort of things. Heartbleed, well, if you believe that security software is secure, Heartbleed might give you pause, because here we've got an attack in open source secure sockets layer software that basically allows a remote adversary to take advantage of a bug in the code to covertly read out memory using the protocol. And this just sort of demonstrates that what you might consider to be a bug or a crash in your software, or just what you would view as being the user, to the adversary, all these things are opportunities. These are vulnerabilities, and if they can figure out how to take advantage of a bug in software and arm it and exploit it, well, they can basically do whatever they want, depending on what that software was. So the other problem we have in the industry is, especially if you look at the defensive products like antivirus and so forth, they're looking for the known malware that's out there. So if, God forbid, someone gets mugged, and they can identify the face of who did it and report it to the police, maybe you could get ABB out, maybe you can get some most wanted posters. Anyway, you've identified that individual. It's not quite that way with malware, as the real world situation is more like getting mugged by changelings, because every time they look different, and that becomes a problem for these signature-based defense methods. Basically, you can repackage the malware, you can repack the malware, there's polymorphic viruses. As everything's attached to the internet, you can get your own custom variety, and the code can change over time as well and start looking different. So the signature-based defenses, which are basically looking for that most wanted poster kind of model, they don't see the new stuff, and they don't see the stuff that was maybe very specifically targeted to individuals or specific companies, as opposed to more general threats. So as an example, malware isn't necessarily that you download an app and run it, or download an executable program and run it. A lot of times you do something that's very innocent, like just surfing the internet or opening a document that really shouldn't cause any problems with the system one wouldn't expect. In this case, we've got a vulnerability that's not quite like the public ones that you've probably heard of before, because it has a very easy to remember name, APSA13-02. I'm sure that will stick with everyone after this talk, as opposed to Heartbleed. So we do need to do a better job, I think, of coining some of these different kinds of attacks. This one happened to be analyzed by
folks in my research lab as well as in McAfee. Now, if you look at some of the popular ones like Operation Aurora, they took advantage of a vulnerability in software, which you might see as a crash. What starts off, that was turned into an exploit. Basically, the adversary has the ability to download data into the system. If you're, in this case, surfing the internet, images and pictures and things like that are basically filling up memory from the browser. And that memory is getting filled up with what is basically instructions, all in the heap, and a lot of it. And the exploit depends on the fact that there's a pointer that's being followed for execution that basically goes kind of random because of a bug. Now, normally that would result in a crash because the pointer just shoots off into memory. You'll probably get a page fault and the program will blue screen or exhibit some behavior that is pretty noticeable. But in the hands of this particular kind of attack, memory is filled up with basically a bunch of innocuous instructions, for example, no-ops in the heap, and when that random execution hits that no-op, it becomes a no-op sled, and the program's executing wherever it landed, and eventually ends up running the code that the adversary planted in the heap. Basically, odds are now they're exploiting the system. Now, hardware technology has at least come to provide some features, or I should say processor technology, to say, well, don't allow data to be executed. That's one way to solve these kind of problems. For example, we saw with Operation Aurora. If the heap has data, then let's not just let that run for any reason, because there might be a bug in the code that actually does then attempt to run that code. So execute, disable, non-executable memory is provided, and the software industry takes advantage of that, and regions of the heap or stack are marked as not executable. So all is good now. Well, no, today we look at a more modern attack, like this one from 2013, which again is very much like Operation Aurora. You've got a document, you open up a document, there's nothing unusual about that. We all do it. This is not an application, executable code, not some malicious executable that was downloaded from the internet. But it's taking advantage of a new kind of attack technique, return-oriented programming. They can't execute off the stack anymore. They can't execute off the heap, but they don't need to because they can actually create a stack of their own. So now that data portion that was done in the heap before, that we talked about, simply becomes what looks like a data stack or a call stack, which is full of a bunch of returns and various values that get passed to different state of the program. And there is another phase of this attack where even with address randomization, where code ends up in unpredictable places, they basically can read out the memory, figure out where the code is they're interested in. This is the legitimate code, but now they're going to make it run the way they want it to. And in fact, to make it easy for everyone to attack these kind of, to launch these kind of attacks, you can go to the internet and actually buy, or not even buy, they're for free, compilers that allow you to basically construct your own ROP gadgets from any legitimate sequence of code to do whatever you want, really. So now you can put together what is data, a call stack, that gets loaded in the heap. Might have been originally an image or something that was downloaded from the internet with the correct sequence of data in it. And there's a bug where you get the stack pointer to somehow pivot now to the heap, or it could pivot to a different region of the stack, that kind of thing. But the point is, it's now returning to these return vectors, which are not legitimate. There was no function calls behind them. They're just piecing together the legitimate code in a sequence that achieves the result of the adversary. And you can actually see for this particular exploit, the point at which the stack was pivoted, and then they were able to start running their own stack from the heap. And once they've done that, there's several other phases that they break out of the sandbox and then are able to launch and load shell code and do whatever else they want to the system at that point. So this just shows you the links of sophistication that the adversary is able to go through. And this is one you haven't even heard about, didn't even make a lot of press, for example. So all that work and no publicity. What's in it for them? So if I were to generalize a lot of the software-based attack vectors that we see today, one simple one is circumvention, where you just say, well, there's a access control API that says, only certain functions are allowed to be executed in sequence, so we'll just bypass that. And return-oriented programming is a good example because I'm not even going through the proper function calls and parameter checking. I'm just getting calls that jump wherever I want to in the code and basically string together the attack I want. Of course, you can always just disable software that's supposed to be monitoring, looking for viruses, that sort of thing. You can change, if you're at a privileged level, say of the operating system, what memory that software sees. So it thinks it's scanning what is the code in memory. It's in fact being redirected to scan some innocuous things, and the real code is hidden somewhere else. You can, of course, do the injection and code modification attacks. If you have the ability to prevent execution, you can deal with some of the injection, but you still have to deal with these various buffer overflows and other common bugs that occur in code that allow the adversary to achieve their goals. And of course, the eavesdropping, the heartbleed kind of model where all you're really doing is observing and then releasing information because you have read access to the targeted data. So the question is, how do we build better protections? And I don't want to simply talk about building moats and castle walls and things like that. I want to talk about how do we build basically a missile defense system, something more advanced where we can layer protections on, including after the fact, including layering protections on legacy code and looking forward to what isn't these kind of old-fashioned signature-based defenses, but how we can actually start observing behavior of malware. So it doesn't matter how you change its code, whatever its malicious objectives were, if you can identify that behavior, then you've identified whatever the malware happens to be in the system. And the way that we do that is you have an app, you have your OS kernel, and you have a processor. What you would like to be able to do is say, from security product, from an antivirus product, for example, that also loads this application, to instruct the processor to monitor for certain behaviors, certain changes to the system, certain interactions that violate policies. And when a malicious app that takes advantage of some exploit changes the behavior of that application, you would like to be able to at least detect that and then notify the security agents, which then might be able to prevent any damage from happening to the system. And moving away from just, oh, I know exactly what the code looks like, and I'm going to create a signature from that, to I know what the code is doing to me, I know what targets they're going after, and I want to detect those behaviors. And that's a way to get around these deficiencies in the signature-based defenses. Now, if you look at the processor technologies that are available today, we've already gone through all these others in the talks. For example, the trusted platform module, Learner went through, trusted launch sequence, trusted, you get the measurement of what you're about to boot as far as the system is concerned to get around certain attacks. Intel TXT is interesting because you can actually relaunch and remeasure throughout runtime and get more than one than just at the beginning of the launch sequence. Of course, virtualization technology, I think we've beaten that to death in the previous talks as well. Great for providing isolation and breaking things up from a security perspective. We also have IOMMU kind of protections for protecting against devices coming in and writing to memory that they're not supposed to, for example. There's a lot of crypto features available in modern processors today. You can accelerate cryptography, so if you want to do faster AES or you want to do faster hashing or RSA or whatnot, there's a lot of support that's provided in modern processor architectures. If we look at building on some of the virtualization technology, aside from just providing multiple virtual machines, what I'd like to get into this talk is how we can actually use virtualization technology to look into that environment you're trying to protect. I don't want to just build these, walled castles and then give up on the what we called in previous talks the rich OS. I really would like to put that missile defense system in place for the rich OS so that it doesn't necessarily fall over in the face of an exploit or an attack. And this is by layering on better protections. Other features like OS guard, which just prevents privileged software from getting confused and executing memory that actually belongs to user space or to applications. Looking forward to architectural extensions that you can look at, buffer overflow protections can be mitigated with some of the memory protection extensions, and also software guard extensions, which I'll get into more, but this is basically technology for providing scalable, trusted execution environments, and much more broadly than just having one castle, but getting a castle for everyone, basically. So if we look at the evolution of memory protections back in the 80s, 90s, when we had protected memory on x86, you had multiple rings defined, and user space as being ring 3, and the kernel or the executive running in ring 0. Everything was great, of course, unless you're in the kernel, because you have the shared address space across, and any exploit there basically means you've now compromised the entire system. We've talked a lot about where virtualization technology is being used to sort of create these multiple environments. So if you didn't think, if you didn't think one OS was trustworthy, how about 2? That should be more trustworthy because there's twice as many. But that's basically the model of isolation that you get by putting a more trustworthy OS next to what you'd consider the rich environment that has lots of third-party code and things that you don't know about running in it. Just because less is more when it comes to security. Now, looking forward at sort of where we can take this from an emerging trends perspective is within one of those rich OSs, can we start overlaying protections, further dividing things up, provide that missile defense system that we're really looking for, so that the peasants aren't just left outside the walls of the castle to fend for themselves, but how do we get a more scalable architecture where we can identify the threats from these kind of behaviors. And this requires some interesting hardware features to be added, or at least architectural features for the processor in order to make this efficient. And we'll call this, just for the talk, getting into the memory views and the register set date and everything else as far as that operating system is concerned, being able to overlay these policies above and beyond what's already part of the operating system. And the goal here is just to reduce the attack surface while minimizing the overhead for providing these new capabilities. Now, it isn't quite as clean-cut as nice little blocks of separate virtual machines with their own environments. When you get into an environment, you have a pretty sophisticated policy. It looks more like a Venn diagram policy. You've got driver components that might want to talk to certain libraries, but not others, so you need to include them in the execution space. But just because 2 software components share the same library for execution, you don't want them to have access to each other's code through the library. So they have an execution view that's shared, but a data view that's separate. And you create these more sophisticated policies depending upon what that software component that's identified needs to be able to do in the system. And even though the protections weren't there before, can you layer those protections on over after the fact by layering them on top? And this way you get to accommodate what's really your attack surface, which is all that legacy code. I mean, it's great that we can provide better protections in the future once we rewrite all the operating systems and come up with new models. But how do you provide protections today is another aspect that we do want to consider. So if we look a little bit more into what the introspection capabilities that virtualization technology gives us is, of course, you can sort of identify different software components that are part of the operating system and figure out what their policies should be after the fact, what kind of behaviors they should exhibit, what code, what data they interact with normally. And basically, your security monitor, which in this case becomes this VMM, can basically track those activities. So as you call back and forth between these different components that you've created, these things can get monitored by the virtual machine layer. And so on. The problem, though, of course, is that's an awful lot of monitoring going on. You're not going to want to be in a position where you're single-stepping everything that's going on inside the operating system. So the question is, what can you do from a processor architecture perspective to eliminate all this additional monitoring by encoding the policy in a way that the processor can just follow along and only report the violations, basically. And we can do that same thing both in the kernel space, but also for applications where there's different dynamic link libraries and components, and you want to create different behavioral monitoring policies on top of the fact. Now, when you look at the hardware for providing some of these things, it's the same good old-fashioned stuff you have for virtualization technology, for creating multiple virtual machines with multiple environments, with multiple operating systems running in. But now we basically turn that model on its head, and we use this for introspection within one environment so that we can provide the monitoring policies. So here you're taking advantage of what are these extended page tables, which were normally used to create memory separation across different virtual machines, and instead you're using them inside one, where you're overlaying these views of memory in order to monitor the behavior of what different components are doing and how they're interacting. And when it comes right down to it, the main performance benefit you can get is by taking advantage of your translation look-aside buffers, which are really where all the paging is being translated, and adding tags, which you're doing anyway for virtualization. But as you're switching different views of memory and you transition from code component A to code component B, you would like not to flush all your processor state in the process, and you don't want to go to the monitor, obviously. You just like the processor to say, oh, you entered at the right point. I've already got that policy. I understand that. I'm going to now switch automatically the paging structure underneath the operating system, and I'm going to take advantage of this other tag in the TLBs, so I won't flush the TLBs, and we'll keep executing as normal. So this way you can create a much faster sled of the separation domains without actually incurring all of this overhead to say, every time something happens in the system, stop, go to the executive, let the executive software figure it out, and then resume. Similarly, when things go wrong, and there is a violation in that encoded policy, which does happen frequently when you're trying to overlay protections on top of legacy software, then you do want an agent to step in and basically determine whether it should fire the missile at the incoming target, or whether that target, in fact, is a legitimate thing, in which case you want to allow it to proceed. And here we can create more efficient exception vectors that basically identify these violations and can handle them very quickly. And that's where the virtualization exceptions come. So again, if we look at the granular isolation mechanism before, with virtualization technologies you'd have before, you would basically be executing one body of code, and then you'd transition to another one. Well, it's in a different memory view, a different extended page table. So you got to go invoke the VMM layer, and the VMM layer with all of its state changes and dumps the processor has to do to get there, needs to run its code, determine whether that was a legitimate transition. If that was a legitimate transition, then it would basically allow it to resume, and you're basically adding a lot of overhead, quite simply, in that process. And this is what we would like to get rid of by encoding it in the processor. So the way that you encode these transitions in the processor is you look at new instructions for virtualization, which go directly to the processor. In this case, we call them VM functions. And VM function 0 is one that Intel has defined, which basically is set up ahead of time, either by the code itself or injected by the VMM, that allows the transitions to be identified in the code and then happen automatically. So that you don't have to invoke the VMM. If you don't go through the VM function, you don't go through the appropriate transition point, then you will get this notification where the executive can spin up. But when you're behaving normally and your function A calls function B as it's supposed to and so forth, all of that should now just become automatic, because the processor at least can see that those are the proper transition points. And this, again, is just being layered on top of virtualization technology. Similarly, you want to get the VMM layer out of the way when you're talking about that guest environment for handling those exceptions, because, again, with legacy software, they will be frequent. So the more that we can do at an architectural level in the processor to minimize the latency for reporting these false positives and handling them and then resuming, the more kinds of protections we can overlay for behavioral analysis. So these are basically EPT exceptions, being if you do have a violation where something was executing in one view but wasn't executable in another, then when you do that transition on execution, you get an event. Now it turns into one of these more efficient virtualization exceptions. And same thing for memory reads and memory writes. And the reason why this is better is because you're taking out all the software overhead for the executives. You're encoding a policy in a way that the processor can follow along, and for 99% of the cases, it can handle it on its own once the executive has set up the appropriate policies. And privilege state changes, all the state dump and save and everything you need to get a different worldview, all the wasted TLB tags that are going by transitioning back and forth between the levels. All of that overhead basically gets avoided. And as we move forward, we want to find ways of making these kind of behavioral models more and more efficient, because the better you can do this without adding overhead, then the more the security vendors can put in place, and the policies that needed to be there in the first place, or new policies that can be overlaid on top of legacy code, become more realistic. You can watch more targets, you can detect more behavioral changes, and basically provide better defenses. The other thing to keep in mind is you want to build your virtualization solutions so that they actually work with virtualization technology, because you have virtualization now for security, for introspection within a single guest environment. If you're running a whole bunch of these guest environments, because that's what virtualization was intended to do originally, you want to make sure that works as well. So designing these things so that they nest well, so that the introspection layers can be set up and run on top of a virtual machine environment without adding any additional overhead, becomes another objective for the processor architecture if it's done right. So if we go back and revisit our attack vectors with these new capabilities that we're putting in place, circumvention we can detect, because if you're supposed to go through the proper entry point function and not just bounce around anywhere you want to in the code, then you've identified the proper entry point in, and that's the only way that the views will switch properly and you'll get access to the data on the other side, or the ability to execute any of the internal functions on the other side. As far as disabling anything that goes and attacks other critical components in the system or tries to change the way that memory is mapped and so forth, these things too can be prevented with the proper behavioral policies in place. Things like buffer overflows, where all of a sudden your code's got out of control and now is impacting somebody else's. This can be detected because those different pages of memory were mapped accordingly and you didn't do the proper view transition to get access to their pages of memory. And of course, with more granularity we get with MPX, you can even define the boundaries down to individual buffers, not just at a page granularity like with extended page tables. And of course, eavesdropping, we've got the ability to identify 3 permission policies, whether it's executable, readable, or writable. And if you want to make sure that view A and view B don't have access to each other's data, then it's a pretty trivial matter to cut that off. If you want to make sure Heartbleed isn't reading out of data that OpenSSL normally would never be reading out of, then you want to create those kind of overlay policies and detect those read events as well to catch those kind of emerging threats. So on to the next phase, which is talking about some of the foundational components that you do want to monitor for behavior, because this is where the rootkits and the advanced persistent threats, these are the things that they're targeting in the system. They need to undermine the scheduler. They need to remap memory. They need to use devices to write over memory in order to inject code or do different kinds of attacks. These are the structures that they want to go after. Obviously, the processor registers themselves, which is well addressed by virtualization technology, because by definition, if you want to mimic hardware or virtualize the hardware, you need a way to control all the processor state that's relevant for mode switches and so forth. So those registers are already monitored by virtualization technology on a selected basis using structures like the VM control structure. Memory mappings is another target where the adversary might go after, because they want to confuse this virtual address and what physical memory it accesses, or they might want to change permissions where they weren't allowed to do something, now they are. They weren't allowed to write to memory, they changed a bit, and now they can write. And then, of course, asynchronous events like interrupts, page faults, all these vectors. If you look at Shadow Walker as another attack hooking into the page fault handler, allowed it to create different views of memory where you were executing the code, but you couldn't read it, for example, because it polluted the TLB going through these different kinds of events. So all of these are the foundational components you want to build on. And of course, you've got the external components as well, like devices that can use direct memory access to overwrite. They also need to conform to the policies that are being overlaid, so you just don't have a device coming in from the side and injecting code into the wrong place. So again, with virtualization technology, processor state is already largely covered. You can determine, for example, that somebody's changed a control register, turned on debug. Any of the MSR registers they can address if they're over or changing where the interrupt descriptor table is, and they modify that register, so on and so forth. All of these things are register changes where you can get an event the executive can run. In this case, we'll call it a security agent, determine whether that was a legitimate change coming from a legitimate piece of software that normally does that, or whether that was, in fact, an attack. And if we look at a few more examples, page table is a great structure to go after. There's a register in x86, the CR3, which identifies basically the root of the current page table that a process is using. If the adversary can simply get into memory and modify the page tables, then they can redirect, change read-only pages to writable map memory however they want. So you actually do want to look at ways of providing these memory views where, for example, only the memory management software is able to access page tables. Other third-party components that have no business touching the page tables shouldn't access. And if they do, then you get the oversight of a security agent to come in and see whether the change was legitimate or not. And again, using this two-level of paging that we have with the virtualization technology, you can actually just say the OS paging structures become become read-only, and they don't become accessible to other components from the wrong software view. And this is a good way to basically provide oversight even into the memory mappings. You can do the same thing for interrupt service routines coming through the interrupt descriptor table, where an interrupt comes, the processor looks up where it's supposed to go in memory to handle that, and then directs it to the right ISRs. You want to make sure that things that aren't allowed to modify ISR state don't get to change the code, but also they don't get to change the data structures, like the table in memory, so that they redirect and interrupt to their malicious code instead of the correct, legitimate routine. And again, there's a register in the processor that you want to track as well, IDTR, that basically tells the processor what descriptor table it's supposed to use for different kinds of interrupts, faults, and other events. And again, by protecting these paths, you're providing a much stronger foundation, because these are the targets that the adversary are often going after, particularly when they want to put in these fundamental attacks. And then it comes down to devices. The interesting thing about devices is, well, they move around in memory, but ultimately they're memory map structures as well. So if you have control over memory, you have ways of now saying, oh, this device is associated with networking, we'll give the network driver access to that device, but not other drivers or other kernel components and so forth. They can't write to the device registers. And conversely, you can use the IOMMU protections to come back to say that device, that's a network device, really shouldn't be overwriting memory that doesn't belong or wasn't allocated by the network driver, for example, in this case. And again, all these protections can get overlaid, and they all generally take the same form. They're memory, and you're tracking it at a fundamental level with the processor. You're switching the views depending on what code is running, what data it has access to. In this case, what device state it has access to as well. So if we look at usages, it's not all entirely, I'm a researcher, this isn't all research and fiction. There actually are attempts going on in the industry. Leendert mentioned deep safe technology and Deep Defender, which is actually going very specifically at rootkits that are trying to undermine the operating system. And there are many other emerging technologies that are using virtualization technology as a way of providing security features within an operating system. And if you look ahead at other things you can do with it, we talked about all the spying software and so forth. When it comes down to, you can protect devices associated with their drivers, provide these siloed stacks that don't allow crosstalk or allow things to inject themselves into it. Then you can start talking about secure input, so the keyboard loggers that are stealing your password won't be able to function. You can protect against these audio attacks where they're listening in on the microphone to hear what you're saying. You can protect storage better so that your master boot record isn't affected or files aren't corrupted, and there's no way to bypass your full drive encryption software, for example, and video and so forth. And literally you can start deciding what the behaviors of software are, overlaying them even over existing operating systems and existing applications so that the malicious behaviors will stand out and can be detected and stopped. Now, while missile defense systems are great in theory, I don't want to leave anyone with the idea that there's no need for a more secure environment, particularly when you look at everything we've talked about being software-based attacks and things that are taking advantage of bugs and vulnerabilities and so forth. The question is, how do you provide a better, more scalable, trusted execution environment? One problem we have with trusted execution environments today, whether you view that as a security coprocessor or a different mode of operation, is they really aren't for everybody. They're not going to scale so that everybody who needs one is going to get one. There's really one, and you kind of have to trust the stack that's in there. And if everybody on the rich OS side says, man, this rich OS is really not where I want to be because it's full of vulnerabilities and bugs and getting attacked, and they all move to the trusted side, you're not really in a better position because now you've got a full-blown environment that is basically a rich environment on the trusted execution side. So generally, this is solved by saying only select folks get to get access to, in this case, for example, the Tower of London. But the rest of the peasants, they have to stand outside and deal with the situation themselves. So when you do get the big one that gets through all these other defenses we've been talking about, how do you create a more scalable environment where basically secrets can be protected for the masses in a more scalable way? The other thing we want to think about in terms of trusted execution environments and how they continue to evolve is how do we reduce the trusted computing base? And the trusted computing base is all that stuff that goes in the trusted execution environment, which is, again, just a separate coprocessor or a separate mode, but it has basically an operating system, and it has to deal with interrupts, and it has all these other same vulnerability points we talked about for the rich operating system, including all the software, firmware stacks, drivers, whatever else you might need in it. So, looking at this pictorially, it's nice that you have a secure environment, but who are those guys standing behind you that can basically see everything you're doing and have access to your secrets now? Especially the guy with the screwdriver doesn't make a lot of sense. What you want to figure out how to do, and what we want to do as an industry, is figure out how we really reduce that TCV so that it doesn't include all the extraneous stuff, and still allow you to basically define your own trusted execution environment for everybody, as it were, that really is minimized to just your code. And that basically means in your trust boundary becomes the hardware, the processor architecture itself. And that ultimately is what you can trust. It would be nice if we didn't have to trust that as well, but then everyone will have to basically get their own sand and melt it and build the appropriate layers and create their own hardware as well. So eventually there's something in the trust pipeline that you have to trust, but you just don't want to have to trust a whole lot of things, particularly third-party components that you may not know. And I think, again, with the OpenSSL attacks, we can see even the security software isn't immune. So today, if you look at what your trust boundary roughly looks like, well, you have the application, which might be the particular secret keeping code that you're interested in protecting, but it's also all the third-party libraries and stuff that are maybe necessary to build that application. You have to trust the system software stack. You have to trust all the way down to the virtual machine monitor, which is basically another complete operating system in and of itself. And of course, you have to trust the firmware and the hardware that's part of that. So if we look at some of these processor extensions that's defined in Intel, and you can look up Intel SGX to see the details and what the ISA might look like for providing sort of these trusted execution environments on demand. The goal is to really extract all of this other software out of the trust boundary. So it's really just the code you want to run on the processor, and the trust relationship becomes the instruction set of the processor and basically what it is able to do for subcomponents within the applications themselves. And this way, wherever the vulnerabilities may come from, whether it's normally in the executive or the system software stacks or through drivers or wherever that happens to be, or even other enclaves, as they're called, cross-talking and injecting code from, you want to be able to basically eliminate all of that. And you want a CPU architecture that can actually define an instruction set that creates these more granular protections that really reduces the trusted computing base just to the core element, the code itself that you want to protect. And once you have this concept of enclaves that come out of the primary processor and its instruction set, you can start taking advantage of all the other instructions that are already part of that instruction set. So all the other security defenses that we talked about before, but also things like the crypto acceleration instructions, for example, AES. So now if you want to build an enclave that talks to another enclave, the nice thing is these things can attest each other. I can verify that the other enclave is the code I want to talk to. Once I've established that, I can now create a trusted channel or a secure communications channel using these other instructions where everything is encrypted for confidentiality, integrity, and so on with respect to those two endpoints. And you can start building more and more endpoints, whether they're local to that device or outside, and they don't really have to have trust in the firmware and the executives and the virtual machine monitors and the operating systems and the driver stacks and the libraries and all the other stuff that's in there. And you can start building these various tunneled networks. And again, you get very cheap, efficient cryptography based on those instruction sets. You get ways of controlling cache and other activities in order to avoid side channels. And you can package all of that up to the specific application code and just that and whatever other code that it needs to communicate with in order to basically build a trusted application. And that granularity is where we see things evolving in the future to provide both better scalability for trusted execution environments, where there's one for all, as it were. At least you can break down the code into just its minimal trusted compute base and not have to take along entire executives and drivers and libraries and all the other extraneous code along for the ride. So just to come back down to the summary in the few minutes I have left, we're seeing that there are obviously increasingly sophisticated attacks. It's getting much more difficult for signature-based defenses like antivirus uses to identify every potential change to malware code or the way it's packed, or the way polymorphic viruses decode themselves in memory. So what we're looking for is, can we provide better behavioral mechanisms at a processor architectural level where we give insight into the fact that code A is interacting with code B in an unusual way. How do we create those kind of different protection domains and observe the interactions between them so that if they ever stray from what is considered the correct policy to something that's potentially malicious, there is a security agent that can actually inject itself into that behavior, observe it, and if it happens to get caught on one of these modern machines that have these capabilities and runs this new software, then you can create signatures for it and go defend much more quickly the rest of the universe where signature-based defenses are really the only option. So it does become a very good sort of cyclic behavior where you can feed back to the larger community once you can identify the brand new targeted attacks that no one has seen before because the new capabilities are starting to get deployed. And then when it comes down to really protecting secrets, how do we evolve the trusted execution environments in a way that there's a trusted execution environment for everybody, much better scalability, a much lower TCB so that you don't have to bring a whole bunch of other software along for the ride and really just trust your code executing within an enclave. And with that, I am finished. Thank you very much.
Thank you, David.
So we just deposit that.
Okay,
Thank you.
great, thank you. So now I would like to end this session with some university research that we have been doing. But first, I think a quick summary. So we talked about the cornerstone security aspects of confidentiality, integrity, and availability. And the speakers spoke a lot about attacks on confidentiality and integrity, password attacks, buffer overflow attacks, and there was also some mention of availability attacks like denial of service and so forth. And the speakers spoke a lot about security mechanisms. So the trusted execution environment in Arm Trust Zone is a mechanism to protect the secret keys when they're being accessed, and the plain text when you finally access the data legitimately and you decrypted it, you better protect the plain text, okay? Leendert talked about isolation methods, which is also a protection method, and virtualization, and David talked a lot about virtualization and introspection. All these are security mechanisms, okay? So now what about university research in hardware security? So what we talked about are the first category of hardware security mechanisms, and that is hardware-enhanced security, where hardware features are put in to enhance the software security and the whole system security, okay? Now, there is a second category of hardware security, which is secure hardware. The hardware itself should be secure. It should not leak your secrets when it's executing correctly, as it does in side channel attacks, okay? Now, we haven't talked as much about this, and I would like to give you a very quick summary of some of the research going on, and then some concrete examples of each of these methods so that you have some feeling of how it works, all right? So first, hardware-enhanced security research. Now, there has been a lot of research on hardware-enabled isolation. So pre-Arm Trust Zone and so forth, there's been the ZOM and AGES and SP architecture and so forth. And all this were all about cryptographic access control and hardware-enhanced security or hardware-enabled isolation methods, where you isolate the trusted execution from the untrusted execution. So all the secure processes that you hear about from academia, or what I sometimes call security-aware processes, are ones that try to provide this isolation, that use cryptography, and that protect confidentiality and integrity through some of these mechanisms you have heard. Very often you have to build it into the TLB and the caches and all as well, all right? Then there's a whole class of research called dynamic information flow tracking that we haven't talked about. And this is done in all kinds of levels, the language level, the compiler level, OS level, hypervisor level, and also hardware level. Okay? So at the hardware level, the key idea is if you want to protect confidentiality, you might have some sensitive information like passwords. So you tag these sensitive information, and you propagate the tag with every instruction. And when the sensitive information is going out on the network or something, you stop it, or you raise an alarm or something, or you go into further software checking, all right? Similarly, if you're trying to protect integrity, where are likely low integrity input coming from? They may be coming from the network. So you tag or you taint that data coming from the network as low integrity. And if that low integrity thing starts to try and call a system call, or write your password file, or change your platform configurations, you better watch out, okay? So you raise an alarm of some sort, okay? An alarm may just mean that you have more software invoked to check this out. So let me give some examples of secure hardware research. So we've mentioned side channels on and off. Leendert mentioned some power side channels, E&M side channels. But side channels is really very scary. This is correctly executing hardware, okay, that is somehow leaking out your information, like your secret keys, okay? This is pretty bad. The hardware is executing correctly. And what computer designers must know is a lot of your techniques for lowering power or for improving performance make the attacker very happy because it makes his life easy, okay? So you have to be careful about that. And then we've talked a lot about how memory is where it all happens, because memory is where transformations take place and so forth. And so you need to protect the memory. You need to isolate memory correctly and protect it correctly. And you need to make sure that the attacker didn't somehow change the external DRAM bits so that what you read in is not what you wrote out, or change it on the memory bus, okay? So remember, we are thinking usually only the attacker, only the processor is the security perimeter in the hardware. External memory is not trusted, should not be trusted. Buses outside the processor are not trusted, or the I/O and networking certainly not trusted, okay? And then there's issue of what about the supply chain? So you've got a good chip, and it goes through all kinds of processes before the chip comes back. What if at some level there, some malicious hardware got inserted? This is like hardware trojans or the hardware version of malware. So perhaps on a certain event, this hardware will start leaking out bits, okay? And it's such a tiny, a few gates, you may not detect it, all right? So how do you protect this? Now, we all know, finally, that CAD is very important. Nobody designs a complex chip all by hand. So you have all these computer-aided design tools. What if the computer-aided design tools inserted some malicious hardware? Okay, how would you know? You trust them, right? What if your golden net list had some hardware trojans inserted by the designer? Okay, so these are all issues in secure hardware design. Another thing that's happening is people take these old chips and they recycle them, but the old chips have very limited lifetime left. So it's built into your new product, and your new product will fail much faster because it's using old chips. Okay, so all these are problems of secure hardware research. And system on chip that uses a lot of IP cores. These IP cores come from all over the place. How do you know they are secure? Okay, that they're not leaking some information that you don't want leaked out. Cyber physical systems is when you use cyber attacks to attack physical systems like the power grid or transportation network, or as you hear in this afternoon, Internet of Things. You attack your home security system, medical devices, so very active research in security of these things. So now, as promised, I'll try and give you an example of each. So let me give an example of secure hardware design first, because we didn't talk about it very much in this tutorial. And the example I would like to give is secure caches that do not leak information. So all of you have probably heard of the heartbleed bug. This is some mechanism called heartbeat that helps you determine availability of systems, all right? Every now and then, that important device will give a heartbeat, okay, that says, I'm alive, I'm alive. Well, this protocol, when put into OpenSSL, into some versions, had some buffer overflow problem, like Leendert described, okay? And it then made it possible to read out some chunk of memory with every heartbeat protocol, okay? And the danger of this is not only can you read out decrypted information, but you will read out the crown jewels of primary keys, the symmetric keys used for your encryption, and the private keys that are used for identity in the digital world, all right, that you should protect, okay? So the problem is after you fix this heartbleed bug, actually the hardware is still leaking out your secret keys all the time. Every single piece of hardware that has a cache is vulnerable to cache side channel leakage. And it can easily leak out a 128-bit key or a 1,000-bit private key, right? So what to do? This is correctly functioning hardware, not like the heartbeat bug where there was malfunctioning software or software with a bug, okay? This is hardware with no bugs, but it's leaking out information. Why? It's very hard for a software solution because things like caches are microarchitecture. They're not visible to the software, okay? They're not directly controllable by software. But a software side channel attack is a software attack on hardware. You don't even need equipment to measure the power emissions or anything. It's just a software attack that could even be carried out remotely over the network, okay? So lots of people have talked about attacks, but very few people have talked about solutions, okay? So our group is one of those that's looked at secure cache solutions to this. How can we thwart the attacker? But we mustn't degrade performance because caches are essential for performance, right? So give you an idea how it works. So I'm going to show a cache, and each line is a cache line here. And red is the attacker processes cache lines. So first, the attacker fills up the whole cache by just reading a large array. So all the lines that belong to the attacker. Now the victim comes in, maybe he's doing AES encryption with a secret key. He needs to use some cache lines, so the victim is yellow. Therefore, when he needs to use some cache line, he kicks out some of the attacker's cache lines. Well, when the attacker comes back, he reads each one of his cache lines, and because cache misses take so much longer time than cache hits, he can tell whether he got a cache miss or a cache hit. If he got a cache miss, he knows that the victim very likely used that line. And because there's a fixed memory address to cache line mapping, the attacker can work backwards and figure out which memory addresses the victim used, and therefore which key bits which affect which memory addresses the attacker used. And then he can derive the whole key. So what's the solution? That's the attack. What's a possible mechanism to mitigate? So what we say is, all right, now the attacker fills up the whole cache. The victim uses a cache line, but instead of evicting that very line, we evict a random line. And this random line can be any one of the cache lines with equal probability, okay? Now, when the attacker comes back, yeah, he detects cache miss on certain lines, but these have no correspondence, no relationship at all to the lines that the victim evicted. And so the attacker now gets no information about what cache lines and therefore memory addresses the victim used, and he cannot go back and figure out the key bits that the victim was using. So it turns out that we have an architecture called new cache architecture, and this it looks exactly like a direct map cache. And the only part that changed is the middle part, which is the normal fixed address decoder, the row decoder, all right? On two sides, you have the data arrays. So here, we've got to do a level of indirection, all right? It's actually a little CAM, content addressable memory. And it takes the address bits, it could map into any one of those cache lines randomly, any one of those cache lines, but only 0 or 1 lines, all right? And then it will read out like a direct map cache, the cache tag and the cache data. So it turns out that this thing actually can defeat those side channel attacks that I talked about. And we actually did a little test chip on this. And on top is the new cache, 32 KB, and on the bottom is the same size, 32 KB, but a traditional 8-way set associative cache. And what you see is that most of the size and the power and all that are these green and red stuff, which is the data array, all right, taking up the size and the power and all this. And the middle yellow part is the tag on the bottom. The address decoder on the 8-way set associative cache on the bottom, and on the top, the tag is smaller on the middle left part, and the cam is a bit bigger. So what this is trying to show is that actually these secure caches aren't much bigger, they aren't any more power hungry, and they actually, with clever circuit design, aren't any slower than your conventional set associative caches. So you literally could pull out an insecure set associated cache, put in a secure new cache. What happens to the performance? Well, it turns out not only the power and the latency are very comparable, but actually the system performance on benchmarks, which were run on both smartphone benchmarks and server benchmarks, is very comparable. And in fact, for some benchmarks, the system performance improves a little bit, okay? Maybe 3% improvement or something. So this is to give some example that if you really do hardware design on this, you can actually get security without sacrificing performance or power or latency, or your overall power, which depends on the number of cache misses as well, okay? So to summarize, it's an example of what is called moving target defense. So what it is if the attacker can attack fixed systems, it's easier for the attacker. Once he finds a path in, he can attack 80% of the systems, and then next month when he comes back, he can find the same path in. So what you want is you want to be a moving target, so the attacker, even if he got in today, he can't get in next hour, or he can't get into an identically configured system, okay? Because there's a moving target mechanism inside. So this is an example of using moving target defense in hardware design. And actually, it's a project funded by DHS, and they would very much like industry to adopt some of these techniques, okay? It's surprising because caches have been studied so much by both academia and industry, and the fact that you can improve the performance even a little bit by adding security is very non-intuitive. Because usually, if you have higher security, you sacrifice performance. If you want high performance, you sacrifice security. But I'm showing you this concrete example that that's not necessary, okay? And it's deployable because technology is ready for industry now. So next, I want to give you an example about hardware-enhanced security research. So I try to tell my students, don't be chasing the tail lights, okay? Most of security is done in a reactive mode. When an attack happens, people scramble to find a defense and close up the hole, okay? But as computer architects, we know microprocessors take, several years to develop and so forth. So you've got to think ahead. So what would be an ideal general purpose security solution, okay, if there's such a thing, all right? And what we said is that you want this solution to be flexible because most of the security world are afraid of hardware defenses because they think hardware is fixed and, it can only deal with certain fixed attacks and not others, but that's not true, okay? What we are saying is that you take software security mechanisms, you build your security mechanisms in software so that they are flexible, but then you protect the software security mechanisms with hardware. Because the smart attacker will go after the security mechanisms done in software before he goes after what the security mechanisms protect, right? Second point is you want finer granularity isolation within the same address space, because very often if you have a security monitor monitoring some untrusted application, if you have to switch worlds, like to go to trust zones secure world, you've lost the context of the address space, and it's hard to do if you're monitoring every instruction or every 3 instructions or something like this. Okay, so you want to protect you want to have the trusted execution environment right there in the unsecure world. And then you've got to be scalable, and the idea is you have to allow many trusted domains at the same time. Citibank doesn't trust Bank of America, but both require trusted e-banking. Okay, so you have to have many security domains available at the same time. And the other thing is, I think David mentioned this, the OS may be an adversary. We hear every week about OS attacks. So how can you trust the OS? Okay, it's a trusted component today that's not trustworthy, so let's just not put it in the trusted computing base. Now, what's under the OS? You may have the hypervisor and the hardware, okay? But don't make the hypervisor so complicated that it becomes like a big bloated OS, and then it will be full of bugs too. So the issue is, let all these rich environments like your Google map run unfettered, and you produce this secure execution environment, like the secure enclave that David was talking about, when you need it, all right? So I won't go into great detail, but the Bastion security architecture was designed exactly for this. It was in HPCA in 2010. And the idea is that you have this hypervisor, which you're going to protect like heck with the hardware. And you want this little hypervisor to be trusted. Now the hypervisor can protect any number of trusted environments above it. Like here we show A, B, and C in different virtual machines within the virtual address space of either the untrusted app or the untrusted OS. Now you've got to provide these trusted environments, A, B, and C, with their own permanent storage, that survives power on-off cycles. So that's shown as, A, B, and B in the disk, which are not segmented areas of this, but cryptographically protected areas of this. Okay? The cryptographically protected areas of disk will protect those areas for confidentiality and integrity, and they will only be accessible like sealed storage, which was the TPM's very clever idea of sealed storage. You can only access that secure storage A when you're executing trusted module A, okay? And even the OS cannot access it, okay? And that's the whole idea. The gray is the trusted parts, and all the rest of the system is untrusted. So, pedagogically, what it is on the left is traditional ideas of every lower layer being trusted and verifying the integrity of the upper layer. And what we are trying to suggest on the right is that you skip these untrusted areas and you still have secure trust chains that are securely rooted in hardware, okay? So on the right, we're skipping the commodity OS as untrusted. Now, how is this good? Well, because it puts in minimal hardware for a lot of scalability of many trust domains. So we have found that really there are two hardware trust anchors needed for secure storage. One is the key, okay, for cryptography to get confidentiality. The other is the root hash, like I showed you, of the hash integrity tree, all right? And so if you provide two new registers in your microprocessor chip, you can protect this large trusted piece of software called the hypervisor and give it secure storage. And now, for all your various different trusted modules, you can have soft registers. These are just memory locations, storage locations in the hypervisor's secure storage. So since these are software registers, there's no limitation, okay? No limitation to how many trusted domains you can protect, no limitation to the size of any domain, and so forth. And so I'm going to skip to the end, but how does it fit into trust zone, for example? So you see, this is like the normal world of trust zone. Trust zone has, in addition, something to the right that is the secure world. But in the secure world, you aren't guaranteed of secure triggers from the normal world. You don't see the context and all. So in the normal world, you could provide more security mechanisms for more arbitrary trusted software modules, okay? And I think this would overcome a lot of the scalability issues and loss of context and performance issues of trust zone, all right? But trust zone is excellent because it has put the stake in the ground and there's a lot of industry ecosystem built up. So let's use it. Let's use trust zone for those really secure stuff like platform integrity and so forth, you know, keys for the platform configuration, how you set up your wireless transmission and all this, and the occasional things like passwords and authentication, do it in trust zone. But in the future, you might want a little bit more flexibility by providing security in the normal world as well. So all I want to say here is that in general, there's a lot of fun things to do in security. On the left, you've got your input devices to the cloud, like the smartphone, the Internet of Things, traffic sensors, and all this. And then on the right, you have all your cloud servers, which may have some security features and some don't. So how do we deal with that? All these existing servers may not have the right hardware security features, but new servers may have some of them. So there's a thing that we can do, which is security on demand. When you go to the cloud for resources, for how many CPUs and how many memory, also say how much security and of what type you want in the SLA, you know, the service level agreements. And then into your cloud computing environment, build an architecture that will assign the correct secure servers when needed, and migrate virtual machines when needed, okay? So to summarize, there's a lot of university research going on, not as much as we would like, all right, but more and more research into hardware security. And some of these are into secure hardware, including the side channels and the hardware trojans and the supply chain security and all this. And we gave an example of cache side channels using moving target defense in hardware design. And then there's a lot of work that's ongoing to make it easier to use hardware to protect software security mechanisms, okay? And system security like I/O and networking and so forth. So in terms of areas, there's lots of fun areas in the client side because security is not only a top to bottom issue, it's also an end-to-end issue. So it's no use if your cloud servers are all secure, but those smartphones that access the cloud are completely insecure. Okay, it's got to be an end-to-end security architecture. And the final thing I want to say is hardware people have a great opportunity, but you have a longer lead time. So it's not that easy to come up with a hardware patch the moment there's a problem. So you have to think ahead. Let's do proactive hardware security rather than reactive security, reacting to every attack, which is why I started out saying, if you want to design a secure system, provide at least the 3 cornerstone properties of confidentiality, integrity, and availability. And you can see that there are examples where this can be very successful without impacting your performance and power utilization. Okay. Thank you. So in the few minutes we have left, we would like to open it for questions, and we would like the other speakers to come up, please. And feel free to ask questions to any of us. Are there people with mics for the questions?
Yep.
Okay.
So, John Massey, quick question. Some of you have sort of addressed this. This is how do you resist attacks from the people that provide you the pieces underneath? And start thinking about that. I mentioned 2 examples. There was Ken Thompson's famous Turing Award lecture about the worm program that used the C preprocessor a long time ago. And there was Werner Vinge's book, Deepness in the Sky, where the hero embedded trapdoors in his dust mote-sized computers that got used by everybody. And the bad guys spent a whole lot of time trying to go through the code to figure out if there's any problem and never could find it. So the question is, there's a lot of layers and pieces and stuff in this. How do we, help make sure that what's in there is safe?
I would just emphasize again that with security, less is more. So the more of that's extraneous, that isn't needed for the trusted code to use, then you just don't want that extraneous stuff in there. And I think it's just going to be, clearly that's the goal and the objective of the industry is to try to remove as much from the trusted computing base as possible, and we'll keep evolving that. But eventually, you have to trust something, right? And that's where we have the certification mechanisms and so forth, just to make sure that what remains is trustworthy.
So yeah, that's what I was going to add to Dave's answer. So in the industry, we actually have things like common criteria, and FIPS is one of them, also another one. And these are methodologies that actually start with the design process, where they actually look at how do you do your design, they validate your design, they also validate the implementation, so they're actually third-party independent testing labs that actually look at your implementation, they look at your source code of everything, they look at your design methodology. So that's to, you're bringing up a good point, right? And it goes back to Ken's Turing Award paper. But we do have design methodologies in place. Now, they are, again, very expensive, so not everybody goes through them. FIPS is less expensive, so more people go through that, also less rigorous, so you do have that challenge.
So I think in the research side of the world, we want to make security verification a lot easier and faster. A lot of security verification should be done at design time, before you've got the chip and the whole system built up. How do you do security verification at that point? It's a whole research area, right? But again, to emphasize what others said, you want the trusted computing base to be as small as possible, so you have a chance of verifying it, okay? Because the larger it is, the more bugs there are likely to be. Other questions?
Trusted computing base, in a way, coming from these commercial vendors, is nothing but security through obscurity, and one would say that obviously the NSA and others have their backdoors. So would the industry vendors commit to an open source peer review of the whole stack of cores and tools and everything? Or is that just not going to happen?
So that's an interesting question. Would we be open to peer review? It depends on who's the reviewer. But yes, we definitely do with certain customers that are concerned about our hardware and whether we have backdoor doors in them, allow them access and review our code. That does happen.
Yeah, from hardware perspective, we pay a lot of attention to our crypto engine, random number generators, anything related to chip ID, etc., to make sure that those things are actually as secure as they can be. But yeah, to answer your question, the industry is evolving to a place where hardware and software and all those things are actually put together to understand that there are no vulnerability left in the system for someone to break into from the back door. So we are trying our best.
So even to open up the software of Trusung and other things would be very helpful, not just open up the hardware.
Yeah,
right.
I agree. But that's a decision that's beyond my pay grade.
Yes, it's difficult. Next question.
Yeah, so I had a question. One obvious counterattack to side channel attacks is to inject random information. So while you're doing the AES computation, you could be generating random radio signals on the side to confound the eavesdropper. Does that cost too much? I mean, why isn't that done? Or is there a power issue? Or
So that is actually done. That is one of the ways to deal with it. The challenge that you still have, depending on the spectrum that you're in for your side channel, right? You can filter it out or not. Yeah. So, but adding noise to it is absolutely the right thing to do. So, for example, with RSA, there is a well-known concept of blinding, where you basically can add a random value to the key, which you can very easily extract at the end. So.
Yeah, and I would just add, it's not free. Obviously, any of these other techniques will have performance. So, I mean, a lot of things like the cache optimizations, well, you can just take over all of the cache, but then you suffer performance for other applications and things, because it's all about how do you get best multiplexing of all these different uses at once to get the performance. So you really do want to make it somewhat customizable. I mean, whoever's writing the trusted code to as much as possible understand how to refactor their code so that if they do need to blind it against side channels, they're in charge, basically. They can make that decision for their application, whereas someone else that might want the performance optimizations, they can take advantage of that.
Yes, so noise is certainly useful to add, and randomization in some sense adds noise, but just noise is not enough, because you can use longer coding, okay, to get out the data. So noise is not always enough, all right? And as David said, you know, some things like cache, if you inject random accesses and all this, you pay the price, okay, of performance. And if you statically partition the cache, then you lose performance also, because even when the other side is not using the cache, you've only got a certain small part of the cache that's available to you. So actually, side channels, there can be, if you have constant operations, you know, that is very hard for the attacker. So some circuit techniques in research, they make such that 0 to 1, 1 to 0 transitions are identical, and you can't tell, okay, whether it's a 0 or a 1. But that requires the circuit to be maybe 2 to 4 times as large, all right? So you pay a cost in area and power and so forth. The other method, of course, is randomization. So just noise is not enough unless everything is noisy. All the accesses are random. Okay.
Just to add to that, for mobile it becomes especially interesting because yes, you can add noise, you can add all those features, but you also want the battery life to go for a
Yes.
day or 2 days, right? So,
Right.
power-aware security is also a very interesting topic that, in theory we can do a lot of things, but how do we do in an envelope of a power budget so that we can still meet the desired, security and still be able to be, run battery-operated devices. So that's very critical.
Right.
I guess what I was wondering is if you could inject the noise just on the critical regions.
Yes.
So you're not going to run the battery down if the only time you're injecting noise is when you're doing the AES key or something.
You can try that, and you just have to make sure that the legitimate use gets the right value, and performance and power are not overly degraded. Next question.
Is there any data showing how much power is consumed by the trust zone processors or the hardware which is used for the security?
I don't have that off the top of my head, but and as I mentioned earlier as well, that the design is so much integrated that it's very, very difficult sometimes to give an overhead example. But if any of you have some ideas on that, it'd be good.
So the question is how much power is consumed by. So I actually think that is sort of an impossible question, right? Part of what the discussion we had here is that security happens at every layer, and you need to do it everywhere. So it really needs to be part of your design. It needs to be built into the way you develop software. It needs to be the way you develop hardware. And I think then it becomes really hard to tease out. I do have numbers for the platform security processor that AMD does, but it's only a tiny segment of the entire solution.
And don't you think that trend is increasing? You are spending more power for the security instead of running the applications?
That particular processor doesn't take a whole lot of power, no. Sort of marginal in the rest of the SoC.
That is particularly scary for the smartphones and mobile devices, and for, in the afternoon here, but this tiny Internet of Things, they are even more power sensitive, right? So one attack is a power attack. If you have a medical device that's run on batteries and you want to cause problems, you drain it, run it so much that it runs out of power. So instead of the hard device being able to last 7 years, now it's going in 1 month or something. That's a big security problem.
And I'd just add, the hardware really helps the most, because if you look at the crypto acceleration features, for example, we wrote a SIGCOMM paper called Encrypting the Internet a number of years ago. When we were originally planning that, people thought that was nuts. Every single search engine query is not going to be encrypted. No one's going to pay for that much overhead. But here we are today, and in fact, when you do search, and all of these other different cloud applications, you are seeing that SSL is used pretty much universally in those. So, and it's growing.
So can we take 1 or 2 more questions? Those who are already up and wanted to ask questions.
Yes, Dr. Lee, you
Yes.
mentioned in the new cache design there were some modest performance gains. Where did the gains come from?
Yeah, what happens is when you randomize the placement in the cache, you can sometimes reduce conflict misses in the cache. And so that's where the gains come from.
Okay, thank you.
So, yes. Any other questions? One last one. Okay.
There's been some recent, if you're talking about encryption, people will do encryption at a very low level or at the application level, but there's some interest now in doing encryption at the TCP level. And one of the problems they've run into is that there's a lot of infrastructure out there that assumes the current structure of the world. And so even though the new protocol would work, it's not, I don't want to say bug compatible, but it violates some unwritten assumptions that are in various pieces of hardware. And you were talking about having hardware acceleration for SSL, things like that. And I'm wondering, could you be inadvertently making life much more difficult for some innovative solutions that are doing encryption at different levels?
Well, I mean, there is already encryption at so many different levels. If you look at the IEEE standards around linksec and maxsec, they're doing it at the link layer basically, and hop by hop encryption. So I think pretty much anywhere you can draw a line in the stack, there is some standardized protocol for doing confidentiality, integrity, and those sort of solutions. But I think it is an interesting question when you look at new algorithms, things beyond AES and so forth. If somebody has their own cryptographic algorithm, how do you get those into systems? Especially when you're talking hardware, that becomes a challenge.
Yeah. I think it's very important that hardware designers working on performance optimization features should understand security. And hardware designers working on power management must also understand security. And we think that is easier than getting all the security guys to understand hardware, because there's a two-way problem. Now, if you take the extra effort as hardware designers to understand the security ramifications of the features you're putting in, you can design performance and power management features that are less vulnerable to attacks, okay? Never none, but less vulnerable.
Great. All right, thank you, Ruby, and all the presenters. An excellent session this morning.